Welcome back to the new section. Now in this section we will understand how to perform the text summarization. Now here as we progress in this video we will see what exactly is this text summarization and the use cases of the text summarization. So let's get started. Now when I say text summarization is a task of natural language processing where I'll be interested in creating the summary of a longer piece of a text, and I want to explain as much as possible using the very limited number of words. That's the overall idea behind this text summarization. And this field is one of the actively pursued by various research groups around the world that we have got. And in order to perform this text summarization, there are various use cases. Some of the use cases of this text summarization are the extractive summarization, which is the auto TDLR bot on Reddit. So what it does is it's a Reddit bot which automatically summarizes the long submissions. And the best part is it removes us the extra example, transition phrases, and the unimportant details and help us in creating the summarization for the given text data. So this is one of the use case of the text summarization task on the natural language processing. Now, apart from that, we see the use cases like, let's say if I want to highlight the news article on the relevant information where I'm creating a summary. So that's one of the use case of the text summarization, and indexing the summaries to reduce the size of the search engine index. So these are some of the use cases of the text summarization. Okay, so now that you have understood what exactly is the text summarization and its importance, let's go ahead and learn about this text summarization in the hands-on manner in the next video. So I'll see you next time. So in this video, as we progress, we will see how to perform the text summarization with the help of Analytica library by writing the code in Python programming language. Now, in the last video, you have understood the importance of the text summarization. So let's understand what is the overall process when we talk about the text summarization. See, whenever we talk about the text summarization, we basically perform the various steps. So the first thing that we do is we are going to extract the paragraph. Okay. First, I'll perform the extraction of the paragraph. So what does this paragraph is contained of? Paragraph, we call it whenever it contains the multiple sentences. So we'll get the paragraph. Okay. Now, once we get the paragraph, the next step that we do is we'll convert the paragraph into the sentences. So we'll convert this paragraph to the sentences. Now, once I perform the conversion, the next thing that I would do is I'll perform the pre-processing on the text data. Here, when I say pre-processing, I'm going to remove the special character and I'm going to remove the stop words, numbers. So I'll do all those things as part of this pre-processing. Now, once I perform this pre-processing, the next thing that we will do is we will apply the tokenization for the given data set. So from the sentence, I'm going to break it down into the individual words. Then interesting part that I would do is I'll go ahead and I'll find the weighted frequency of the occurrence. So I'll find weighted frequency of occurrence. Now, once I find this weighted frequency of occurrence, the next thing that we will do is we'll replace the words by weighted frequency in the original sentence. Here, when I say weighted frequency of words, I can find the weighted frequency of each word by dividing its frequency by the frequency of most occurring word. Okay, that's the overall idea about this weighted frequency. Now, let me just give you an example to understand as how do we find the weighted frequency of occurrence. So let's say I've got 5 words in a given text document. So I've got the words as like, Harry, movie, love, okay, and let's say hate. So these are the words that I've got in my overall data set. So first thing that I'll do is I'll calculate the frequency. I'll calculate the frequency of my individual words. Let's say the word hate is present one time like is present 2 times, Harry is present once, word love is present 5 times, okay, in the overall data set, and the word movie is present 3 times. Now what I'll do is, to calculate the weighted frequency, I'll first find the maximum frequency in this given data set. So the maximum frequency is actually 5. So I'll keep this 5, which is my highest frequency. I'll mention my frequency as 1, that is the overall frequency value, weighted frequency, as 1. So for 3, I'll divide 3 by 5. So that is 0.6. 1, this is equal to 0.2. 2, it is 0.4. 0.2. So in this way, I'm going to calculate the weighted frequencies. Okay, so I'll go ahead and calculate the weighted frequencies. Now, once I calculate the weighted frequency of my individual tokens in a given sentence, next what I'll do is I'll replace the words by the weighted frequency in the original sentence. Let's say I've got the word like, I've got the sentence like this: Harry, movie, good. And there is another sentence that says as Harry, hate, movie. So let's say these are the two sentences that I've got. Now what I'll do is, if I've got these multiple sentences in my paragraph, okay, for each sentence, I'm going to replace it with weighted frequencies. So for the word Harry, what is the frequency? Weighted frequency 0.2. For movie, it is 0.6. For good, it is, let's assume there is one more good, and which is having the frequency as 1, which is 0.2. So 0.2, which is equal to 1. And I'll calculate the same thing for the Harry hate movie. Harry 0.2, hate is 0.2, movie is 0.6. So I'll get the overall sum of weighted frequencies for, that is for my individual sentences, as 1. So this is one of the final step. So this final step is what I'll be doing is, I'll plug the weighted frequency in place of the corresponding words in the original sequences, and I'll find their sum. Okay, so it is very important that the weighted frequency for the words removed during the pre-processing, let's say the stop words, punctuation, if it was present in my sentences, I'll just be equal to 0. So therefore we'll not consider it during the addition purpose. Now once we perform this activity, the next thing that we will do is we will perform the sorting. Okay, we will perform the sorting. So here we will perform the sorting sentences in a descending order. Okay, so I'll just sort the sentences in a descending order. Now once I sort the sentences in the descending order, we'll set some threshold value. Based on the threshold value, we are going to generate the summarization. So that's the overall concept behind this text summarization. It's a very simple concept. This is how this text summarization is going to happen whenever we make use of NLTK library. Now the advanced libraries such as the transformer architecture, so there the way it would work is entirely different. Now in this scenario, the way it would work is little different. Okay, that's the main difference, team. All right, so now that you are aware of this, so let's go ahead and perform the text summarization from the Wikipedia. In order to do this text summarization using Wikipedia, so what we will do is, first thing, I'm going to install the Beautiful Soup 4. So pip install Beautiful Soup 4. So this is going to install the Beautiful Soup library, which will help me to perform the web scraping activity. So it says it's already present. And another thing that I want to install right now is LXML. So pip install LXML. So I'll be requiring this to parse the HTML and the XML file. Now let's go ahead and scrape the data from the website. So what I'll do is, I'll start by necessary imports. Import bs4 as bs. Okay, next I'm going to import url lib dot request. I'll import regular expression. Here I'm going to scrape the data from the Wikipedia. So scrape data is equal to urllib.request dot URL open, and here the website that I'm going to refer is the Wikipedia site for the machine learning. So this is the website data that I'm going to perform the web scraping right now. Okay, so this is the website. So URL open, I'll just mention my website. Now once I mention the data, so I'm going to extract the article, so which is nothing but scraped data dot read. So this is going to scrape the article from this Wikipedia site. Next, we are going to perform the parsing. So I'll say parsing is equal to bs dot beautiful soup. Okay, bs dot beautiful soup article comma lxml. Okay, so once I extract the article, next I'm going to extract the paragraphs. So paragraphs is equal to parsing dot find underscore all, and I'll mention the tag that is p. Okay, next what I'll do is I'll just go ahead and perform the concatenation. So I'll say my text from article is equal to, I'll just define it as a blank string, and then from here I'll write as for p in paragraph. Okay, so inside this I'm going to say text article, and I'll perform the simple concatenation with p.text. So this will just go ahead and perform the activity. Okay, now once this is done, so this will help me to extract the data. So what I have written right here is, so I have imported the necessary libraries, and here I'm making use of this URL open function from the URL lib.request utility to scrape the data from the Wikipedia site. Next, I have made use of read method, and this read function on the object returned by URL open, I have actually used it to read the data. Now in order to parse the data, I have made use of this beautiful soup, and I have passed it this scrape data, that is my article, and the LXML parser. Okay, now in the Wikipedia article site, so all the texts are actually enclosed inside the p tag. So in order to retrieve the text, I have made use of the find all function on the object written by the beautiful soup. The tag name is passed as the parameter for this function. The find all method is going to return all the paragraphs in the article in the format of a list. So all the paragraphs have been combined in order to recreate the article. Now once that is done, if I just go ahead and display my text article, see, this is my text article. So the same text article that you see right here in the Wikipedia site, the same thing have been extracted from this overall website. Now let's go ahead and perform some pre-processing. So this is one of the first step whenever we are working with the text data. Now this Wikipedia references are generally enclosed within the square brackets. So what I'll do is I'm going to create a regular expression which will remove these square brackets and replaces the resulting multiple spaces with the help of a single space. Okay, in order to do that, I'll make use of the regular expression, and this is how it would look like. So here my text article, if I execute this, this would now contain the text without the bracket. Okay, so that is the overall idea right now. The next thing that I can do is I can go ahead and perform the data cleaning. So in order to perform the data cleaning, I'll just go ahead and I'll remove some special characters and the digits. So in order to do that, I'll also take the help of regular expression. Let me just compose the regular expression and I'll show you. So here I've made use of the regular expression. So this will take care of removing the special characters and the digits. Now once I've removed it, next I'll just go ahead and I'll convert this text into the sentences. So we have got the paragraph. The first thing that we have to do is we'll have to perform this conversion of this paragraph into the individual sentence. So in order to perform this activity, we've got NLTK library From there, we can make use of the function send tokenize. So let's go ahead and do the same. I'll start by importing the NLTK library. Okay, next I'm going to say sentence list is equal to NLTK dot send underscore tokenize, and inside the parenthesis I'm going to mention my text article. Okay, this will just go ahead and remove the this will just go ahead and perform the activity of tokenization. Okay, so we can just go ahead and perform this activity. Now once we have performed this activity, we can then go ahead and find the weighted frequency of the occurrence. Now this is very important. Here, this text article that we have got, okay, this text article that we have got, this contains the full stop and all those things. Okay, this contains a full stop. Here, this pre-processing where I have removed the punctuation and special characters. So whenever we are performing the tokenization, I'm making use of the original text. The reason because this contains the full stop, and that will actually help the overall NLTK library to perform the sentence tokenization. Now, the next part, that is finding the weighted frequency of the occurrence of my individual words. There I can make use of formatted text article. Okay, so this is the code that will help me to perform this activity of finding the weighted frequency of the occurrence. So this is how it would look like. So here what I have written is I have got the stop words from the English language, and then I have created a loop. Okay, I have created a loop. Now in this loop, for individual words that I have got after I perform the word tokenization over here, so I'm checking if it is not present in stop words, and if it is present over here, I'll just increase its frequency as 1. If it is not present, then I'll just set it equal to 1. Okay, so this will help me to count the number of occurrences for the given words. Okay, so that's how we do it. Now in order to calculate the weighted frequency, so what I have to do is I'll just have to go ahead and find the maximum out of it, and once I find the maximum, then I can just go ahead and divide it. That will help me to get the weighted frequencies. So which is nothing but the code that would look like this. Here I've got the maximum of the word frequencies, and once I have the maximum, then I'm going to divide it by that maximum frequency. That will help me to calculate the weighted frequencies. Now once we have this value, then we will go to our individual sentences and perform this calculation of the sentence score. So let's go ahead and perform the calculation of the sentence score. So now observe this code. For each and every sentence that I've got in my sentence list, first I'll perform the word tokenization. For individual word, okay, I'll calculate the sentence codes for my individual word from the word frequencies. So the sentence score, if I now display, okay, so this will help me to display the individual sentence as well as its respective sentence score. Okay, so first I have actually created the sentence score as the dictionary. The keys of this dictionary will be the sentence themselves, which is what I have ensured right here. Then the corresponding value is the word frequency value of my individual word. And as it progresses, as it goes through each and every token, I'll perform the addition. Now, if I want to generate the summary, now this is an interesting topic. So if I want to generate the summary, there is a library that's called as HEAPQ. That's the library that we use it. So here, what I'm doing right now is, so I'm generating the summary. So I'm saying it as HEAPQ, and from this I'm calling the function that is called as nlargest in order to retrieve the top 7 sentences with the highest score. And the overall output summary looks something like this. It says semi-supervised learning falls between unsupervised learning without any training data set and supervised learning with completely labeled training data. Robot learning is inspired. See, you can clearly understand what exactly is this is all about. This overall text that we have got is all about talking about the machine learning. So what we have done is we have summarized the text corpus from this entire Wikipedia article into a very short paragraph so that we have directly performed the text summarization. And we'll talk about the text summarization again in the final section when we talk about the Hugging Face transformers. But I hope this gives you an overall intuition as how the text summarization can also be performed using the basic libraries such as NLTK library. It's a very simple concept. So mathematically, it's very easy to visualize and intuitively understand as well. We'll extract the paragraph, convert the paragraph into the sentence. We'll remove special characters, tokenization, find the weighted frequencies of the occurrence, and we'll replace the sentences with the weighted frequencies. Then we will sort the sentences in a descending order and we'll just go ahead and perform the activity of summarization by getting the top 7 or whatever that we would like to call. All right, so I hope you guys have enjoyed, and I hope you now have a clear understanding about the concept of text summarization. So I'll see you next time. Welcome back to your learning journey. Now in this section, we'll be performing an NLP project which is analyzing the tweets from the Twitter website. So the application domain is the social media domain. So as we proceed in this video, we will look into the importance of social media, the applications of the social media, and then we'll also look into the understanding of the task at hand. So that's the overall journey that we are going to follow in this video. So let's start by understanding the importance of social media platform. Now, as you know, the social media platforms have revolutionized the way we communicate with the individuals, groups, communities, corporates, media houses, so on. It has changed the way and it has revolutionized the way that we communicate with each other. And if you look into the statistics, there are 152 million monthly active users are available on Twitter with 6,000 tweets per second. Now imagine the volume of data that is being generated each second. And it clearly says there are 2.5 billion active users on Facebook with 57,000 posts per second. Now imagine the same with the Instagram and the other social media platforms. So with so many communications that are happening right now in all the social media platform, and in all the social media platform, people are expressing their view in the natural language, which actually results in amazing application building on the topic of natural language processing. The applications of natural language processing would include trending topic detection, opinion mining, sentiment detection, rumor or a fake news detection, and the customer support. So these are some of the common applications that we can perform from the data that we can extract from the social media platform. Now in this hands-on project, we will see how we can analyze the tweets from the IPL cricket team in real time, and we'll also perform the sentiment classification on the data that we have extracted from the Twitter website. So that's what this entire project is all about. I hope you guys are excited. I'll see you in the next video where I'll show you as how you can set up your Twitter developer account. So see you in the next video. So in this video, let's go ahead and set up the developer account for Twitter. In order to set up the developer account in Twitter, you just have to visit the URL developer.twitter.com. So let me just show you the demonstration. I'll just go ahead and create it in front of you. So I'll go to this URL developer.twitter.com, and here in the screen, click on the sign up button. Now in the sign up page, mention your email address and everything. I'm just going to mention my email address right now. Now once it's done, so we'll have to go ahead and work with the same. So I'll start with the account creation. Okay, I'll use my email address.
Then we'll set up some account right now. Okay, then I'll click on the sign up. Now once it's done, this will ask me to authenticate. I'll click on authenticate and we'll complete the authentication. Okay, now it's asking me for some verification code. Let me just get the same. So verification mail is received. We'll complete this process and now it's asking me for a password. So okay, just go ahead and complete the activity. Okay, so I'll just go ahead and set some username and we'll complete the sign up process. Okay, so this has created the account with Twitter. Now it is asking me to sign up for the developer portal. So which means if you already have a Twitter account, you can log in with the existing Twitter account and apply for the developer account. If you do not have it, you have to create a Twitter account, and post that you'll have to submit the form. So I'm currently submitting the form as of now. Okay. Okay, so it's asking to have a verified phone number. Let me just ensure that my profile has the same. I'll do this activity team, and once that is done, we'll complete the same. We'll have to go to our Twitter account. Okay, so once you perform the addition of the phone number and complete the entire setup, so what you can do is you can click on the developer portal and see whether you have the access to this developer portal. So this is a page that you should be able to access it once you have set up your developer account on Twitter. Now this will take some time, team. So generally it will take 24 to 48 hours to get your developer account created and deactivated. Now once that is done, you'll be able to proceed with the further step. Alright, so with this, we come to the end of this video. Now as we proceed in our next video, we will get started and we are going to understand about the library that's called as Tweepy, which we'll be using in our hands-on project. So I'll see you next time. Now continuing in our hands-on implementation, now in this video, we will understand the basics of Tweepy and I'll demonstrate you as how you can work with the Tweepy library and interact with the Twitter application. So let's learn as we progress. Now let's start by understanding what exactly is this Tweepy. Now Tweepy is an open source Python package which gives us a convenient way to access the Twitter API using the Python programming language. Now this Twitter's API is actually well documented one, and that is one of the great place where you can start creating your own data set. So in order to create a data set and get the most of this Tweepy library, first thing that you would require is the developer account. So we have it already created. Now to experiment with this Twitter developer account, what we would require is we need some authentication. So for that, we have to create a chatbot. So currently, I think this is a basic chatbot that I already have. If not, you'll get an interface which will ask you to create a new project. So once you create the project, you can just get started. So I'll give you an example. Okay. So here I can click on project and overview, and from this screen, you can actually create the various application. Okay, I'll just go ahead and click on add app, and then from here in the screen I'll click on the button that says as create new. Next it will ask me to select an app environment. Now for the demonstration purpose, what I'm going to do is I'll just go ahead and select it as development. Okay, I'll just select it as development right here. That's the app environment that I would consider. I'll click on the next button. Now here it is asking me to specify a name. I'm going to mention it as NLP hyphen chatbot. Okay, that's the name that I would mention. Okay, you can give any of the name as per your request. For now, I'll just mention it like this. I'll click on the next, and here this is going to return me the API key secret, and the bearer token. Ensure that you note this down because this is important for us for communicating with our Google Colab notebook with the Twitter account. So let's go ahead and do that. I'm going to note this down right now. So this is my API key, then API key secret. Okay, and then we'll create the bearer token. Okay, and then once we create the bearer token, so we'll just go to the dashboard. Now, along with this, we also require some tokens. So in this page, it says set up your account. Your app settings page will allow you to enable third-party authentication, get user tokens. So if you're unable to access this app, so what you can do is from the left hand side, you can check on the app that you have created. And in this page, okay, in this page, we are interested in generating the keys and tokens. I'll click on this option that says as keys and tokens. And from here, I'm going to generate the access token and the access secret. So I'm going to click on generate, and this has generated me an access token. Okay, and then access secret. So this is also very important. So this is my access token secret. I'll just save it right now. Okay, now the reason that we are saving it because we will be referring these whenever we are creating the connection between the Google Colab with this Twitter website that we have got. Okay, now once this is done, I'll start by creating a new notebook. Now I'll click on new notebook in this Google Colab page. Now I'll start by installing the library that is TWP. So pip install TWP. So by default, the Google Colab has this TWP library. So if it's not there, you can use this command to install the TWP in your local system. Okay, now once that is done, okay, once the installation of TWP is done, next we'll go ahead and perform the authentication. So here, while performing this authentication, we can make use of OAuth. Now this OAuth is very simple process. So here, what you have to do is, I'll just create 4 variables. I'll write it as access token is equal to, here, whatever the access token that we have got, we'll just paste it right here. So here, this is the access token. Okay, next we'll specify the other values. So here for the access secret, I'll mention the access secret that we have noted earlier. Okay, just ensure that you define it as a string so that it is easier to work. Then I'll mention it as consumer key, and this is equal to the consumer key that we have created. That's our API key. Okay, next we have something called as consumer secret. Now this is nothing but the API key secret. So ensure that you note this down and define it in an efficient manner to avoid any issues. Now, in order to set up the access to the Twitter API, I'm going to create a method that's called as def connect to Twitter, and I'll say it as OAuth. So this is a method that will be called, and whenever we call this method, I'm going to write it like this. I'll say auth is equal to, I'll import my TWP library. I'm going to say import TWP. Okay, next here I'll say TWP dot OAuth handler. Okay, and inside the parenthesis I'll have to mention my consumer key and consumer secret. Then after this we have to set the access token. I'll say auth dot set access token, and inside the parenthesis I'll specify my access token and the access secret. Now once this is done, we are going to call the API. So API is equal to TWP dot API, and I'll mention my auth object. Okay, next what we can do is every time whenever we are calling this function, this is going to return this API. Okay, this is going to return this API. Now what we will do is we'll create an API object like this. I'll say connect to Twitter. Okay, so I'm going to execute this. So here, once this is done, we can just ensure that whether it is working or not by displaying some of the tweets from the home page. So this is an example homepage that I've like my example Twitter account that I've got. From this Twitter account, I'm going to display the latest tweets. So what I can do is I'll say public tweets is equal to API dot home underscore timeline, and inside the I'll just call this method. That's the method that we can access. Then I'll say for tweet in public tweets. Okay, so here I'm going to display the individual text. So if I display, this is the output that I'll get. Currently I'm not seeing anything. The reason because I do not have any tweets in the home page. Since it's a newly created account, I do not have much tweets over here. Okay, I do not have much tweets over here because it's a very new account and I have not set it up itself, and that's the reason that we do not see it. So let's do one thing. Let me just specify something and let's see what we could get right now. Okay, so currently we do not see anything in the home page right now. Okay, so this is the high level test that we have performed. Let us follow few members from the Twitter, and I'll click on the home again. Now in the home, I've got some entries right here. Now let's execute the code right now. See, whatever the tweets that you see in the home page of Twitter, the same thing is being displayed right here in this page. So it says we are working for peace and development in Tripura, and that is somewhere over here. Yeah, see, we are working for peace and development in Tripura. So whatever the tweets that you see in my homepage, the same thing is being returned over here from this code. So this would confirm us that the Twitter account that we have got is working expected, and the credentials that we have generated from the developer account, it is able to communicate with the Twitter site and it is able to generate the outcome for us. Okay, so that's how we can get the random tweets which are currently available in the home page. Now let's assume that we want to get the tweets from a specific user. So let's select a specific user. So I'm going to select the user. Maybe I'm going to get a tweet. I'm going to display the tweets from the Elon Musk. So this is his Twitter ID @ Elon Musk. So let's go ahead and get the tweets that are present in the Elon Musk timeline. So what I'll do is this time I'm going to say Elon tweets is equal to API dot user underscore timeline, and here I'm going to mention his ID, that is Elon Musk, for tweet in Elon tweets. So here I'm going to print tweet.text. Okay, so I'll just execute this. See, this has returned the various text from the Elon Musk tweets. So there are a lot of tweets which are reply over here, which has been done over here. So the same thing that is present in the Twitter site is being returned for us. Okay, that's the overall idea right here when we talk about getting the tweets from the specific user profile as well. So in this way, we can get the tweets and we can perform the analysis. Okay, now what we can do is, as we progress in our future session, we will get these tweets from the various IPL teams and we will go ahead and apply some sentiment analysis on this given tweets which we perform the data mining from the Twitter website. So with this, we come to the end of this video. Now as we progress in the next video, let's look into the hands-on project implementation. So I'll see you next time. Now that you're aware of how to work with the VP library, now in this video, let's perform the NLP project where we'll be analyzing the tweets from the Twitter account. So let's look into the project implementation in this video. So let's start coding. So I have already written the entire code of this project, and I'll demonstrate as how exactly that we are going to perform this implementation of extracting the data from the Twitter. So first thing that we are doing right now is, so here the first thing that we are going to do is we are going to install a library called Vader Sentiment. Now this is a library which I'm currently installing it so that this would help me to perform the activity of sentiment classification and the text analysis. So we'll just install this Vader Sentiment. Now, once that is done, we are going to take care of necessary library imports. So I'm importing the TWP library. I'm importing the pandas library. I'm importing the plotly for creation of plot and importing the NLTK for performing the natural language processing related task. The stop words from the NLTK. Tweet tokenizer. Now this tweet tokenizer is a special tokenizer which we generally use it whenever we want to perform the tokenization of the tweets that we extract from the Twitter. Then I'm extracting the stop words, which is in the English language. Then from the Vader sentiment library, I'm importing the sentiment intensity analyzer. We'll talk about it as we progress at the end of this analysis. Then I'm importing the regular expression, matplotlib pyplot, and some color maps. And then I'm importing the word cloud for creation of visualization. And after that, yeah, I think after that I'm importing the time module. Now, once the import is complete, here I'm making use of the same code which we have written earlier, where we are making use of OAuth and making use of the access token, access secret, consumer key, and consumer secret. And we are setting up the connection with the twitter.com, and then we'll create an API object. Now, once this is done, so in order to test whether it is working or not, so here I'm updating my user status with a text as this is an automated test tweet using Tweepy. So let's come to my Twitter account. So this is my Twitter account. Okay. So the latest tweet was November 21, 2022. Now the today's date is 3rd February. Now let's go ahead and update the same. So this is an automated test tweet using Tweepy from NLP course. I'm going to execute this cell. So once I execute this cell, okay, so this is going to perform the activity of posting. So currently my application do not have the ability of posting. So in order to modify this, what we can do is we'll just come to our application that we have created, that is NLP chatbot, and from here we'll modify the settings. So I'll modify the settings in this application. So here click on the edit. Now we'll modify the same. So currently it says it is created with read-only permission under the keys and tokens. Now in this scenario, in order to modify the settings, click on the projects on the left hand side, select the project, and here in this page, click on the user authentication settings, select the option of setup, and here ensure that you select the option of read, write, and direct messages. Okay, and it is requesting for some callback URI. Just mention some any URL. So I'll say manifoldlearning.in. Okay, just I'll mention some random URL, and it is asking me some website URL. I'll mention the same, and then look into the other options, whatever it is asking. Ensure that you make the settings. Click on save. So I have made those changes over here. Now it is mentioning my client ID and client secret. So let me just replace those values into my code. So this is my client ID. Okay, client secret. Okay, next we'll just come to our app. We'll regenerate it. Okay, I'm going to perform the regeneration. This time once I perform the regeneration, I'm now having all the access. I'll copy this access token. Okay, this is my access token, and then we will have the access token secret. Okay, I think I had copied in a wrong account. Let me just paste it here. I'll execute this. I hope it is successful. Now we'll re-execute this cell. Okay, we could not be authenticated. Let's revalidate it and mention it. So let me just do it again and we'll retry. Okay, so access token secret. Next, we will make use of the bearer tokens. Okay, so this is my bearer token. Anyways, bearer token is not required. So we've got the API key and secret. Okay, let's regenerate the API key and secret. So this is my API key and this is my API key secret. Okay, now let's revalidate it. That's amazing, guys. So this was successful. Now let's test it. If I refresh my page of my Twitter account, see, I've got a message that says this is an automated test tweet using TWP from NLP codes. So this confirms that we are able to connect our Twitter website, that is our Twitter account, from this Google Colab notebook. Now it's a great thing. Now what we are interested in this project is we are interested in extracting the IPL team's tweets. Okay, so IPL is nothing but the Indian Premier League. So Indian Premier League, which is the cricket, which is a T20 cricket league which happens in India, and it is contested by 10 teams based out of 7 cities and 3 states. Okay, so like we are just collecting the tweets from the various teams who plays inside this IPL, that is the Indian Premier League cricket website, cricket match. Okay, so we are just noting down their Twitter handles. Okay, now what I'm going to do is for each and every IPL team, I'm extracting top 300 tweets from their page. Okay, I'm extracting top 300 tweets from their page. Okay, so I'm going through each and every tweets that I've got. I'm extracting their tweet ID, tweet text, favorite counts, retweet counts, and all those information, the metadata that we have got from Twitter. So I'm extracting all those information for the each and every individual tweet. Then I'm appending it over here for this tweet list as a Python dictionary. Okay, so this is going to perform the extraction of the data from the Twitter side for each and every IPL teams that I have mentioned over here inside this Python dictionary. Now from this data, we'll go ahead and create a data frame, and if I display the first few entries of this data frame, this is how it would look like. I've got the IPL team, I've got the tweet ID, text, favorite count, retweet counts created at. So all these information that we have extracted from the individual tweet. Now to help you understand what exactly it is, let me just show you. Okay, if I just update any tweet, okay, once I update any tweet, it's going to perform the activity. Okay, so here, see, it is generating the metadata as well. So if I search for text, see, the text attribute is referring to the text that I have actually posted. And apart from that, there are various attributes that we have got, which we are getting as a response from the API of Twitter. So we are referring the same and we are accessing the information in this variables, and as a result we are creating a data frame which holds all these details. Now if I display the shape of my data frame, the overall shape of this data frame is 1300 rows. Okay, so this is the total shape of the data frame that we have got. So for the working purpose, currently I'm going to save it as a CSV file. So this will help me to export it into an external file which we can further use it at a later point. Next, here I'm creating a copy of this variable and I'm storing inside the variable called data. Then I'm trying to get a visualization about the value counts. Okay, now this is a plot which will help me to get the information about which device the people are actually using. So here, in order to do the same, from the column of source is a column which has the information as from which system the users have actually tweeted. Okay, so based on that, we have created a visualization over here. So from this, we can see that all the IPL teams are actually tweeting from the Twitter, that is from the Twitter web app. Okay, now this is one of the EDA that we have performed. Okay, so Twitter users actually performs the like usage from the Twitter web app. That's great. Next, here we are trying to perform the aggregation of the IPL team on the basis of retweet count and the favorite count. Okay, then we are creating a plot. So here we can observe that the favorite counts is very high for RCB, followed by Chennai Super Kings, and this is followed by Mumbai Indians and so on. So it looks like the RCB team is much active in Twitter. RCB and Chennai IPL, these two teams are much active in Twitter. That's what we can observe from this given data, and the fans are also liking the same. Okay, next we are trying to extract the hashtag. So this is a function which is going to extract the hashtags from the various tweets that we have extracted. Next, I'm extracting everything as a tags. Next, what I'll do is I'm just trying to understand what are the commonly used hashtags. So here, in order to implement this, we are directly making use of regular expression and its related abilities in the Python code, which will help us to work with it in an efficient manner. See, these are the various hashtags, and we also have the information as how many times that particular hashtag was used. Okay. Next, once that is done, we can go ahead and remove the user handle. So normally when we are extracting the data from Twitter, so we can, it also comes with the user handle. So we can remove those user handle information as well. And then after we remove those user handle, so in this given data, we do not have much user handle, but if you're extracting something from a company, then you might get those information over here, and this regular expression will actually remove those user handle. And if you have any links, we can remove those links. This is another regular expression that has been created. Then once that is done, so we can see, just observe in the previous text, okay, without fix we had the HTTP link. Now after apply the application of this regular expression, we have removed that link. And in the same way, we'll go ahead and remove the special characters. Now once the special characters have been removed, next we'll proceed with data tokenization and removal of stop words. So we are just performing the tokenization, and I'm removing the stop words from this given data. And for efficiently perform the tokenization, I'm making use of tweet tokenizer. Okay, now we can actually use the same and perform the tokenization. I think in this given data, we have made use of split itself, but you can also apply this tweet tokenizer in order to improvise the tokenization efficiency. Okay, that's the core principle. Like we can just use this to improvise the tweet tokenizer. Then we can up here we have actually performed the data pre-processing, and once that is done, we are applying the lemmatization on this given data set. Now once we perform the lemmatization, we'll perform the pre-processing, and then this will take care of rejoining, lemmatization, and cleaning the words. So once we have done all the pre-processing, now in order to check the sentiment, we are making use of a library that is called as Vader Sentiment. Now this Vader Sentiment is a library which is also known as Valence Aware Dictionary and Sentiment Reasoner, which is a lexicon and a rule-based sentiment analysis tool. This is the library that we are using. And if you come down, it clearly says how to interpret the output that we are getting it over here. So whenever we get the output, this is how the overall output we would get. So we'll get the pause score and the compound score, and along with that we've got neutral and the negative. So the compound score that we would get, it is computed by summing the variance scores of each word in the lexicon adjusted according to the rules, and normalized between -1 and +1. So if I have any value closer to -1, it's the most extreme negative, and if I have any value closer to +1, it is most extreme positive. Okay, so this is the overall idea, and neutral is -0.05 to +0.05, and negative is less than -0.05, positive is greater than +0.05. So this is how we classify the sentences as positive, neutral, or negative. Now, once this is done, okay, so here in this scenario, we have initialized the same, and to calculate all those output, I'm creating it as dictionary, and I'm saving it inside the out variable. Now, if you look into the out.keys, see, we've got negative, neutral, positive, and compound. So now we are just performing the aggregation of the IPL team by mean. Now this is a plot that we are creating to get to know about how the overall sentiment of the individual teams would look like. So the this New Delhi, so the New Delhi is the one, their tweets are much of the neutral in nature. That is what I would observe from this given data. And compound score of 0.5, I think positives are highest for RCB. That is what we observe from this overall scenario. Now, since the activity that I'm performing is not in the IPL season, we do not see much of the celebratory wins from the various IPL team. Now, if you run the same code during the IPL season, that is when the Indian Premier League match starts, then at that time you might see a different kind of results as well. So since we are performing this analysis live, being this off season, this is the overall pattern that we observe from this given data set. And we can also create the word cloud where we can create the visualization about what exactly is the various things that is happening. So what we are doing is we are representing the negative in reds. So wherever we have got the negative sentiment, it is represented in reds. Wherever it is positive, it is in greens. So when they are celebrating or when it is positive, the hashtag that is famous is Whistle Podu, Play Bold, IPL Auction, Yellow Love, Team India, Tata IPL. So these are the various hashtags that are currently trending when they are expressing the positive. Okay, so in this way, we can make use of the word cloud as well to represent the overall text data. So with this simple project implementation, you have now understood the importance of social media, how we can extract the tweets from the social media site, that is twitter.com, and how we can make use of the Vader sentiment, and along with the text pre-processing which you have learned already in the previous sections, combine everything and perform the sentiment analysis on a real-time data set. Now in this example, I have made use of a simple approach when it comes to text cleaning. Now you can take it to the next level by including the cleaning processes for the given domain data that you might be working with. All right, team. So with this, we come to the end of this section. So thank you so much for watching. I look forward to seeing you in the next video. In this video, let's talk about the NLP transformers. Now, transformers has changed the way that we process the text data. Now, this transformer is actually a new architecture. Now, this architecture aims to solve this task of sequence to sequence while easily handling the long-term dependencies. Now, the main idea about this transformer is, or the main reason that this transformer came into picture is, when we talk about the natural language processing, we'll be dealing with a lot of text data. Now, throughout your learning journey, you have actually learned about the various ways to process this text data and perform the pre-processing and then generate the analysis from the processed text data, where in this scenario, representing the text in the numerical format is being taken care by us. Now, what happened was, so people started using the deep learning approach. And one such neural network that came into picture is the recurrent neural network, which is capable of remembering what has happened in the backend. That means what has occurred in the past. So with that with that architecture of recurrent neural network, we had an issue of long-term dependencies or the long distance dependencies. Suppose if I've got a text that says as the movie is good. So here in this scenario, when I'm processing each word at a time, so at that time, the last word when I come across the word as good, I was unable to connect to as to which thing that I'm saying it as a good. So it is unable to understand the dependencies between the word good with the word of movie. Now from the human perspective, it seems like a very easy task, but from the machine perspective, it's a complex activity. Now, this was some of the challenges that we had with the sequence to sequence model, which is nothing but the deep learning based approach of recurrent neural network. Now, what has happened in the future days was the architecture of this transformer was actually released. So with this architecture of transformer, so we were able to represent the text data in a numerical format and also remember the long-term dependencies as well. If I want to describe the basic architecture of transformer, so this slide describes the basic architecture of the transformer. So the transformer will have the encoder and the decoder. So using this encoder and decoder architecture, we are able to learn the important information from the text data. Now this encoder is responsible for getting the source data, and decoder is responsible for getting the transform data from the encoder and generate the prediction. So that's the overall idea about the transformer architecture, which is a encoder decoder architecture. Now if you simply look into this architecture, it seems it's a very complex architecture, but don't worry, it's a very simple one. And as we progress in the learning journey in the upcoming sections, it will become clear to you. Now, in order to dive deep into the transformer, it is very important that you get a little intuition about the recurrent neural network, the encoder decoder framework, the attention mechanism, and the transfer learning in NLP. So it's very important that you understand these things, which are the backbone of the NLP architecture, that is the transformers, which are the new trend or the new advanced architecture that we have got right now. So as we progress in the next video, we will understand what exactly is this recurrent neural network, how it is different from the general neural network that we have got, and then we will proceed ahead with the further learning journey. I'll see you next time. So in this video, let's understand the concept of neural network. Why is it important? And what is the core principle behind this recurrent neural network? So that's the learning journey in this video. So let's understand the same. Now, throughout your learning journey till now, you have actually made use of machine learning. So using the machine learning concept, so you are able to learn the patterns that are present in the data set. So when we talk about machine learning, one key feature that you have to remember is, in case of machine learning, so we are going to work with the data set. So if I want to describe how does the data would look like, assuming that this is one column of the data, and like this I've got multiple columns in my data set. Okay, so each box over here represents the input. Okay, and along with the representation of these inputs, so I also have an output data. So this is my y, which is my output. Okay, and we will have the features. I'll call it as x1. Okay, we'll call this as an x1, x2, okay, and the x3. So these are the three features that we have it on our data set. Now when we talk about our text data, so we will also have a similar pattern, isn't it, guys? So x1, x2, x3 is nothing but the individual words I might have in my vocabulary, or it could be the word embedding representation of my individual words. Now when we are processing the data, the way that we have processed the data is we have represented these inputs, that is the features, in a numerical format. Okay, once we have represented the features in a numerical format, what we were doing is using this x and y, we were applying a machine learning model. So assuming that this is my machine learning model, so I was actually applying this entire data set on this machine learning model. The idea is by the application of this machine learning model, I'm able to learn the patterns between X and Y. So the intention is learn the patterns between input and output. So this is what we were doing till now. So finding the patterns between input and output, that's the core idea of machine learning. Now what happens is, in case of machine learning model, the way that I'm going to learn from the given data set, it is dependent on the complexity of the machine learning model. So we've got various machine learning model. Now let me just name some of the common machine learning model for classification. We've got logistic regression, decision tree classifier, and we have got naive Bayes, and we also have the algorithm called KNN classifier, that is K neighbors classifier, and we have an algorithm called the random forest, bagging model, boosting model. So these are the various types of machine learning algorithms that we have got right now, where I can send my data, that is X and Y, having the features represented in a numerical format, apply this data on this machine learning model using the various options that I have got with me. And then once I apply the machine learning model, so I'll be finding the patterns between X and Y. This finding the pattern is dependent on the complexity of the machine learning model. For example, in case of logistic regression model, so I would expect that the data is linearly separable, and then linearly separable. So that's one of the key thing. And another thing is, it expects that there is I can divide this data set by drawing a kind of a linear plane. So that's the intuition behind this logistic regression. And the same is the scenario with decision tree classifier. Now while working with decision tree classifier, there are very high chances of overfit as well. And while working with naive Bayes algorithm, it has the assumption that my features are actually independent of each other. And KNN classifier, if I'm using this technique, so one of the disadvantage that I'll have is like I'll be saving my entire data set. Now once I save my entire data set, I'll be finding the distance from my new data point to the entire training data set. So computation will be very slow in case of KNN classifier. And coming to random forest algorithm, this is little better because here we are applying the bootstrapping and the aggregation in this scenario. So bootstrapping plus aggregation. Okay. So as a result of this, we'll get an advantage, but still this is not of, I would say, the foolproof solution. So what it has resulted is, okay, researchers have come across with a flexible algorithm where we can increase the complexity as per our requirement so that we can effectively learn the patterns that is present in the data set. So that is where the deep learning came into picture. So the deep learning is a subset of machine learning. So if I want to give you these notes, I'll say this as a subset of machine learning. Now being a subset of machine learning, what I'll be doing right now is I'll be finding the patterns that is present in the data set with what we call it as a artificial neural networks. So I'll be making use of the artificial neural network in order to find the patterns between my input and output, that is X and Y. Okay, I'll find the patterns between X and Y using this artificial neural network. So as a result of this, the advantage that we get is, so since we are now using the artificial neural network, the advantages is can now learn the complex pattern in the data set. So here with this neural network, we are able to classify the image in a much better way, and we are able to learn the complex pattern in a data set and can fit the data into any domain. And another advantage that we have come across when we are using this deep learning technique is in this scenario. So what we have found is, so like when we are making use of the deep learning algorithm, there is no feature engineering required, or feature engineering or feature learning, so or feature selection. So feature selection is required because everything will be taken care automatically. So these are some of the uh, major advantage that we have seen with deep learning neural networks. Now, if I want to show you the pattern of this deep learning neural network and describe the parts of this deep learning neural network, so this is how a typical neural network would look like. Okay, I'll take you with a screenshot so that you'll understand what is happening in case of neural network. So if I draw this, so this is how a neural network would look like. So in this scenario, we'll have the inputs at the start. Okay, we will have the inputs. I'll call this as x1 and x2. Okay, so x1 and x2 are these two inputs. So what I'll have is I'll have the connection between my inputs. So assuming that I have it here. So this is one input. Okay, this is one input and this is another input. So I have two input in this example. Okay, these two inputs are connected to a neural network. These boxes that you see right here, these boxes we call it as an individual neurons. Okay, these are called as individual neurons, and in this layer we call it as an individual layer. So this layer is called as the first hidden layer, because this is the first layer that I see. This is my first hidden layer, and the next layer that you see next to it is the second hidden layer. Okay, this is actually my second hidden layer. So I've got x1 and x2. So we call x1 and x2 are the inputs. So overall, the data that we call it as an input layer. So in my input layer, I have two inputs, x1 and x2. This input layer is connected to my first hidden layer, and in my first hidden layer we have four neurons. Each box represents my individual neuron, hence you see this over here as 4 neuron. And in my second hidden layer I've got 2 neuron. So overall in this scenario I've got two hidden layers. Okay, I've got two hidden layers, and then at the end I will have an output. Okay, so assuming that the output is one output, I'll call it as y. So this y output that you see right here, we call this as an output layer. So in case of deep learning neural network, we'll be dealing with input layer, hidden layer, and the output layer. These are the parts of my deep learning neural network. Now, having these deep learning neural network which look like this, the best part is using this complex neural network or the structure that you see right here, we are able to learn the complex patterns that is present in the data set. Now let me illustrate the power of deep learning to you. So I'll take you through the example. So this is the neural network playground. Now for the demonstration purpose, so I have got two inputs, x1 and x2. Okay, these are the two inputs, and I have got one hidden layer in this example, and there is one neuron. Okay, so here the pattern that we observe in this data set is there is a concentric circle. And for the activation function, I'll make use it as sigmoid. So this overall structure is the simulation of logistic regression model. So what I'm trying to do is, with this given pattern of concentric circle, I'm trying to split the data set or split this concentric circle, which are having two classes. I'm able to represent those classes with the help of a single logistic regression model. Now think about it. Is it realistically possible to perform the activity of classification using the logistic regression model? So just think about it. See, when I say logistic regression model, I'm interested in drawing a straight line. So I can draw a straight line like this. I can draw a straight line like this. So no matter where I draw the straight line, I will not be able to find the patterns in this data set and split the data in an efficient way. So this is the major challenge that we see right now with the help of a single logistic regression model. So we call it as a sigmoid model from the neural network perspective. If I do the training as well, see, once I press the play button, this training is taking place. Now it has created a decision boundary and it has drawn a decision boundary right here. Now with the decision boundary that you see right here, so one major thing that we would observe is, so the model is not able to separate the classes in an efficient way. There are a lot of misclassifications. So in this region especially, there are a lot of misclassification. The orange data points is being classified as the blue data points. So there is a misclassification that is being taking place. Since there are a lot of misclassifications that are happening in this scenario, so what we have to do is we want a better model. So what I'll be doing is, as I mentioned, the deep learning neural network is capable of learning the more complex patterns in the data set. So let's try to validate it whether the statement is correct or not. So what I'll do this time is, instead of having one hidden layer with one neuron, I'm going to increase the number of neurons. So I have that same two inputs in my input layer, but this time in my input layer, in my hidden layer, I'm having three neurons. And in the output layer, this is how it would look like. Now I'll just begin the training and I want you to observe the overall outcome. If I just click on the play button right now, see, I'm now able to learn this pattern in an effective way. So what it clearly proves is that the deep learning model is capable of learning the complex pattern in the data set, provided I've got the sufficient number of neurons in my given data set. So if I've got the sufficient number of neurons in my neural network architecture, then I can learn the complex pattern of any shape from the given data set. So that is the overall idea, and that's the advantage of this deep learning neural network. Now, with this thing in place, okay, so we were able to learn the complex patterns in the data. So what we have now understood is, so I'll just come up. So instead of using the machine learning model right now, so what we can now do is, so we can send that, we can actually send the entire thing, the data that I've got, into this deep learning neural network. Okay, I can send my data into the deep learning neural network. I'm able to learn the complex pattern in this data set. Now, this theory is good, but there are some challenges that we have got, especially when we talk about the natural language processing. So let's look into the challenges that we have got in applying the deep learning, that is the deep learning neural networks that we have got. Challenges of NLP with deep learning neural network. So this kind of architecture that you see right now, so this is actually known as feed forward neural network. Okay, this is known as the feed forward neural network. The architecture that I've shown you, right? This is actually known as feed forward neural network. So what is the challenges that we have got in NLP if we are applying this feed forward neural network? So let's understand the same. See, one of the major advantage that we see right now in if we are using this deep learning neural network for NLP is the way that we are processing the data. So just think about it. Let's say I've got a data set. Okay, I've got a text data that would look like this. The text data says, so dog was crossing the road and it was very tired. Now, when I have this text that would look like this, okay, if I ask you what is this word it would refer to? So as a human being, if I ask you what is this word is actually referring to? So obviously, as a human being, you can say that, hey, this word it is actually referring to the word dog. Because as a human being, it's very easy for us to say, okay, this word it is actually referring to the word dog. But when you think about the data set and dividing the text into the individual features, so what does it mean? So what we'll be doing is, instead of having the each and every word. So what we'll be doing in case of natural language processing, which you are aware of it already. So you know that I'll be representing the every text that I have got with me with the help of a vector. So I'll be representing the individual word in the format of a vector. So I'll be representing it in the format of a vector. So each word will have some vector representation. So individual box represents the individual vectors of my individual words. Okay, that is what it would mean. So for the demonstration purpose, I'm just using some boxes like this. So think that this is the vector representation of my individual words. All of them will have the same length. Okay, so these boxes are nothing but the feature vectors. Okay, I'm going to generate the feature vectors from the given text data. Now, once I have the feature vectors represented, with this feature vectors represented, and so these feature vectors will now become X, and I will have some output. Okay, I'll have some output data. Maybe I'll call it as this will be my output that I want to predict. Okay, this will be my output that I want to predict. Now, in this scenario, when I'm finding the relationship between X and Y, so I'll be processing the entire X as a whole, and I'll not be able to learn the representation between the words that I have got in my sentence. So are you able to follow along with me? So when I have got the feature vectors for the text data and I have got the Y, when I apply the model, okay, so let's say that I'll apply the model right now. So it could be machine learning model or it could be deep learning model. Let's say deep learning model itself. So when I apply a deep learning model by sending both X and Y for my given data set. Okay. So in this scenario, okay, when I apply this X and Y as a given data set, I'll try to learn everything as an individual feature. So this will be one feature. Okay, I'll call it as X1. Okay, I'll call it as x1. Okay, and likewise I'll have x2. This will be my x1. Okay, so then likewise I'll have x2, x3 and so on. So I'll be treating my individual features, and the overall concept is each feature will be independent. Each features will be independent when we are applying this feed-forward neural network. So dog will be one feature, was will be another feature, crossing will be another feature, the will be another feature, road will be another feature. So each and every word will be the individual feature that we will have, and it will be treated independently when we are finding the patterns between the features and the target. Now, when we are working with the text data, so we have to ensure that there is a relationship between the individual words, so which we are unable to find it with the help of this feed-forward neural network. So here in this scenario, in order to learn these patterns between the words, the way that we process the data should be changed. So, which means I cannot simply go ahead and make use of this existing feed-forward neural network. So we have to find a better way to process these kind of text data, which is capable of remembering as what has actually happened in my previous feature, considering that it should be able to process the text data. So we are in requirement of a neural network which is capable of processing my previous features as well as understanding its relationship in the next word. That's the overall idea, or that's the overall goal right now. So the goal or the wish list that we now have is, the goal is find the neural network. Okay, find the neural network architecture which is capable of remembering, okay, which is capable of remembering my previous input or the previous features. So, or the neural network which is capable of understanding, okay, the features are not actually independent, features are actually dependent to each other. So
That is the kind of a neural network that we are looking out for. So that kind of neural network, okay, so that neural network is called as a recurrent neural network. So recurrent neural network is a type of neural network. It's actually another type of neural network. So what we will do is, in the scenario of the recurrent neural network, we are going to get the data in a specific timestamp. We process the data in the format of a timestamp. Okay, while processing the data in the format of a timestamp, so each time when I'm processing the timestamp, or each time when I'm processing the individual data, I'll I'll be processing the current data as well as understanding what was my previous outcome. So that is how we will be processing the data in the scenario of recurrent neural network. Alright guys, so now in this video, you have understood what are the challenges that we have got in the feed-forward neural network. We'll stop the video over here. In the next video, let's see what exactly is this recurrent neural network and how is it majorly different compared to the feed-forward neural network and why it is so special. So I'll see you next time. In the last video, we have looked into the challenges that we have if we are making use of feed-forward neural network for the purpose of natural language processing. So the solution is recurrent neural network. So let's understand what is so special about this recurrent neural network and how does it process the data. Now in the scenario of this feed-forward neural network, the way we process the data is something like this. I'll be sending the features independently. As you can see in this example, so x1 is being sent independently, x2 is also being sent independently. Both x1 and x2 are sent independently together. Now on this data, we are going to perform the data transformation here. When I say data transformation, I'll take the dot product between them and I'll apply the activation function. And at the end, I'll pass the data through various layers. And at the end, we'll have an output layer which will help me to determine the output. So the core thing that you have to remember is, in case of feed-forward neural network, the data is processed independently. So the important thing, this is very important thing, I'll mention it here in the notes as well. In case of feed-forward neural network, features are processed independently. So this is what we would observe. So features are processed independently. Okay, so but we have to find the relationship between the features as well. So let's see how we can do that. So when I say finding the features independently, if I take the same example representation which we have used earlier. So suppose if I have the text that says as dog was crossing the road and it was very tired. So I'll be processing my individual word that I have got as the individual feature and I'll be processing it independently. Okay, that is the overall idea scenario of feed forward neural network. Now in the scenario of this recurrent neural network, the way we process the data is entirely different. Now to help you understand this, so what we will do is, in case of recurrent neural network, I'll be processing my individual words in a sequence manner. So if I call this as the entire collection of words, so I'll be processing individual words at a time. For example, I'll take the first word that I've got with me. Okay, this is the vector representation of the word dog. Okay, so what I'll have is I'll have the word dog. So using this word dog, I'll have the vector representation of the word dog and I'll send this word dog as an input for a neuron. Okay, I'll send this as an input for a neuron. And if I want to represent that neuron, so this is a neuron. H, which is my hidden representation. I'll send this as an input for this neuron, the vector representation, and I'll get some output from this hidden representation. I'll call this hidden representation as Y. Okay, so I'll send this hidden representation as Y. So the next thing that I will do is, like once I process this text, okay, once I process this word of dog, the next thing that I'll do is I'll process the next word. So I'll have the same kind of network architecture that you see right now. Okay,
I'll have the same kind of network architecture. I'll call this as H0. Okay, and above 1 I'll call it as Y0. Now this time I'm going to send in the next word, that is the was. Okay, was is my next word. I'll send the next word over here as an input, and this word will be having its vector representation. So here, while getting the vector representation, I can make use of any technique. I can make use of word embedding or TF-IDF vectorizer. I can use any of the method. So using that vector representation, we will generate the hidden representation. But most importantly, yes, while generating this hidden word representation, not only it will consider my current word, but there will be a connection. Okay, there will be a connection between my H0 and H1. So the output that I have generated, that is H0, will also be sent as an input when it is generating the output for the second word. So this connection is called as a recurrent connection. So this is the recurrent connection. Okay, and this process repeats. So to illustrate the same for the other words, I'll have the representation something like this. Next, I'll be processing the next word, that is crossing. Okay, crossing will be the next word, and this is going to, while calculation of my H2 in this scenario, I'll consider my H1, and then I'll be generating the output as Y2. So you can clearly observe how the connections are happening in this scenario. So then the word the, and while processing the word the, I'll also consider to find the output of H3, I'll also consider my previous output, that is H2, and I'll generate the output as Y3. So this is the kind of structure that we will have in the scenario of recurrent neural network. So this recurrent neural network has a special architecture where what it will do is it will feed back the input in order to predict the output of the layer. So when it is generating the output for the second word, that is second word that I have got right now, when I'm trying to do this in that scenario, so what we will have is, so it will also use the output from the previous word. Now this is the idea of recurrent neural network. Now this general way of recurrent neural network, I'm sure it would be confusing to you. So let's do one thing. Let's consider the various use case, and let me show you how does the overall network architecture would look like. So what we will do right now is we will look into the types of recurrent neural network that will help you to understand how does this recurrent connections would be, and then we will look into the types of the other concepts of training. Okay, so when we talk about the types of recurrent neural network, so one type is called as a one-to-one architecture. Okay, this is called as a one-to-one architecture. Now in the scenario of this one-to-one architecture, it's known as the vanilla neural network. What we generally use it is, so we will use a single input, and for the single input we will generate a single output, which means this part. So the applications of this one-to-one architecture is next character prediction or next word prediction, next word prediction or next character prediction, next character prediction. So these are the applications of this one-to-one architecture. For example, if I send in the input as dog, I would expect what will be the next word. Like in this scenario, the next word will be the vector representation of the word was. Okay, so this is the typical kind of application that we'll be looking at in this scenario of one-to-one architecture. So next, the next step will be something like this. Next step is getting the input as was, okay, predicting the next word as an output, that is the crossing. Okay, so this kind of architecture, so where the application is a scenario of next word prediction or next character prediction given an input word, so this kind of architecture is called as a one-to-one architecture. So in the scenario of this one-to-one architecture, for each input I will have the each output from the individual neuron. So these cells, that is blue cells that you see right here, these are all called as a RNN cell. recurrent neural network cell. Okay, this is the application and the working of this one-to-one architecture. Now, apart from this one-to-one architecture, there is another kind of an architecture that's called as the many to one-to-many architecture. Okay, let's see how does the one-to-many architecture look like. So in the scenario of this one-to-many architecture, this is a type of neural network where I will give a single input and I'll be generating multiple output. So the application of this one-to-many architecture is image caption. So image captioning is one of the application of this one-to-many architecture. So let's understand how does this one-to-many architecture would look like. So here in the scenario of this one-to-many architecture, I will have a single input. Okay, I'll just have the single input, and this single input is capable of generating the, or from the single input I'm interested in generating the multiple outputs. For example, if I input any image, okay, if I input any image, suppose the image is like this, which is a image which look like this. Okay, so I'll be sending a single image as an input, which is one input. Okay, I'll name this as an input. Okay, and I'll use this as an input and I'll be generating multiple outputs. So the output can be something as captioning the image. So is cat is sleeping now. So here what I have done is, using a single image as an input, I have generated multiple outputs. So this kind of architecture is called as the one-to-many architecture. I'll take a single input, and using a single input, I'm generating multiple outputs in a sequence. Okay, so this kind of architecture is called as a one-to-many architecture. So if the task is to generate the output for each and every input, that's an one-to-one architecture. If using a single input, if I want to generate multiple outputs, then it's a one-to-many architecture. So this is how the one-to-many architecture would look like. So using a single input as X, I'll generate the H0, which is my hidden state, and Y0 is the output at my current state. And using my H0, I'll again generate one more hidden state and will calculate the Y1. Okay, so in this way, the one-to-many architecture would look like. So similarly, if we progress and create the other, look into the other aspects of or other types of architecture, the other architecture that we will have, the third type of architecture is a common architecture, which we call it as many to one architecture. Okay, it's called as many to one architecture. So this is a common type of architecture which we use it in natural language processing task. The application is sentiment classification. So in this scenario, I'm interested to take multiple inputs. For the multiple inputs, I'm interested in classifying a specific class. For example, if I've got a text that says as movie is good, okay, so here using these three words, okay, I'm interested in generating the single output. So if I want to represent it, so this is the illustration of many to one architecture. So as you can clearly see, I've got a sentence as movie is good. So each time, at each timestamp, I'll be sending my individual words as an input, and at the end, for the final word, I'll be generating the output, which will classify in this example whether this given text sequence belongs to a positive sentiment or not. Okay, so this kind of architecture is called as a many to one architecture. And lastly, there's another kind of architecture which is called as many to many architecture, which is called as a many to many architecture. So in the scenario of this many to many architecture, the application is machine translation, which is also a natural language processing task. So in this scenario of machine translation, so what happens is I'll be getting multiple inputs. Okay, I'll be getting multiple inputs, and using my multiple inputs, I want to generate the multiple outputs as well as a sequence. For example, if I have the input as coffee is good, okay, if this is my input, and let's assume I want to generate the output, I want to generate the output in which is the output in a different language, which is a typical machine learning task, then it would be something like this. Suppose the task is conversion from English to German. Then, so what I'll do is for each input, I'll be generating H0, H1, H2. Then using my H2, I'll go ahead and generate the output in the other language. So maybe I'll generate the Y3. Here the Y3 is nothing but cafe. Okay. And I'll call it as H4. Okay. Cafe ist gut. So here in this scenario, this is an example of many-to-many architecture. I'm taking multiple inputs and then I'm generating the multiple outputs. So this kind of architecture is called as the many-to-many architecture. Now this many-to-many architecture is also known as encoder-decoder architecture. Okay, this is also known as encoder decoder architecture. The reason that we call it as encoder decoder architecture because here the input in one language is being processed and I'm generating a hidden state representation. So this H2 that I'm generating, this has the information of both H0 and H1 as well, which combines the entire information that I have got in the source data, and then using this information I'm trying to generate the output in the other language. So this is my encoded data, and using this encoded data I'm decoding it in the other language. So this is also known as the encoder decoder architecture. So these are the various types of recurrent neural network architecture that we have got. So in this recurrent neural network architecture, the core idea is we will be sending the data in a sequence, okay, where each input that I have got, okay, is being sent to my neuron, and when the next input or the next word in the sequence is getting processed, so it will remember what has happened in the past. So what was my previous input, and based on that the outputs will be calculated. So using this format, we are able to learn the relationship between the features in an effective way. So that is the advantage of this recurrent neural network. Now this recurrent neural network has the applications in natural language processing, that is like sentiment classification, image captioning, that is text generation. It is used in machine translation. It can be used in time series prediction. So the applications are limitless. But we have the issues with this recurrent neural network. So what are the issues that we have got? So the issues in recurrent neural network is, so one major issue, which is one of the major challenge that we have got right now is this. It is vanishing gradient descent or vanishing gradient problem. So what happens is, if you think about it, let's consider this example. If you consider this many-to-many architecture, when I have the output at this timestamp, that is cafe, so at this point, if I want to update my parameters, then I'll have to come backwards. Okay, I have to come backwards in a sequential data, and which means this H3 is made up of H2, H2 is made up of H0. So as the networks goes deeper and deeper, the initial layers will not get updated. The gradients becomes small and small, and as a result of this, the learning of the long data sequences will become difficult. And the another challenge that we have got with this recurrent neural network is exploding gradient problem. So this is the other scenario. If the slope tends to grow exponentially instead of decaying, then in that scenario we actually call it as an exploding gradient descent, and this would raise when the large error gradients accumulate, and this would actually result in large updates to the neural network. and as a result of this, my model weights will not be able to converge. So these are the problems that we have got with the recurrent neural network. Now, for solving the problems of exploding gradient descent, so we have found some solution. So if I represent those solution for exploding gradient descent, maybe proper initialization. So using this initialization technique, we can reduce it, or truncated back propagation. Applying the truncated back propagation will also help us in reducing the issues related to exploding gradient descent and gradient clipping. So these are the possible solutions that we have got for the exploding gradient descent. Okay, so this is the one way. So I'll mention it in orange color. Okay, now when it comes to vanishing gradient descent, so the ways that we can actually reduce this vanishing gradient descent problem is, so initialization, gradient clipping, choosing the right activation function, usage of proper activation function. And the another way that we can reduce the issues of vanishing gradient descent problem, which is one of the major problem, is usage of LSTM neural network, which is nothing but long short-term memory neural based network. Okay, so these are the ways in which that we can reduce the issues of the recurrent neural network. So you have looked into the problem, and the solution is one way, or the architecture that we got it as a solution is the LSTM neural network. So this LSTM neural network will help us in reducing the disadvantage or the issues that we have currently faced with the recurrent neural network. So let's understand what is the advantages that we are getting with this LSTM neural network. Okay, so let's see how this is beneficial, which will give us more intuition in solving the issues with the recurrent neural network. So let's see in the next video, guys. So in the last session, you have understood that what are the disadvantages in recurrent neural network, and the solution is LSTM neural network, which is a special kind of neural network. So let's understand what's so special about this LSTM neural network. First of all, let's understand the full form. So LSTM is nothing but long short-term memory neural network, which is nothing but the long short-term memory neural network. So this LSTM is a special kind of recurrent neural network, and this is capable of learning the long-term dependencies. One of the main challenge that we had with recurrent neural network is when the sequence becomes bigger and bigger, my network was not capable of learning the long-term dependencies, that is dependencies from the previous word to the current word. This was one of the major challenge with the recurrent neural network. Hence, so researchers analyzed this, and they came up with a solution that is called as the long short-term memory neural network. And this network has been specifically designed to avoid the long-term dependency problem. So here, when we talk about the recurrent neural network, so in the scenario of recurrent neural network, it's a chain of processing of the data set. It just processes the data from one neuron to the another neuron, which is a chain-like structure, which we have seen earlier. But what we will do is, instead of direct H0 that you see right now, inside that network, so we make use of various gates. Okay, we make use of various gate. So you don't have to learn deep about this LSTM neural network, because we are not going in deep from the NLP perspective, as we are currently using the transformers and the other logic. But let me just give you a quick idea about what is happening and why it is an important, and why it is a best one compared to the recurrent neural network. So in this LSTM neural network, we deal with various kinds of gate. So the first step, or the first gate that we have got, is the forget layer, or the forget gate. Okay, the first gate is what we call it as a forget gate. So let's understand what exactly is this forget gate. Now forget gate is this individual part. Okay, if I want to highlight it, so
I can just highlight it and show it to you. So this highlighted part that you have seen, that I've just did highlighted right now. So this is my core forget gate. Okay, this is my core forget gate. Now, what is the role of this forget gate? Is the forget gate is to just forget the things which is not relevant for me while processing the current input. Okay, this is responsible for removing the unnecessary information before it gets the new data. So that's the overall idea right now. And the other gate that we have got is the input gate. Okay, this is the other input gate that I have got right here. Now here, the input gate responsible for getting the input, and whatever the information that is present in my current input state, that will be calculated and it will be added for my long-term memory. Okay, so here the input gate is the next gate that we will have. Okay, so we will have the input gate. The input gate is responsible for getting the current input and processing the current input data and adding it for my long-term state. And then we will have one more gate that's called as the output gate. The output gate is responsible for getting the data of my current state. Okay, it is responsible for getting the data from my current state and generating the output at my current timestamp. So these are the important gates that we will have in the LSTM network. So with the help of all these gates, we are able to effectively process the data. Okay, so this is the overall idea behind this LSTM neural network. We have got the forget gate, which help me to forget the things which are not important for me. We have got the input gate, which takes the current input and then generates the output. And we have got the output gate, which will generate the output at my current timestamp. To help you understand this, suppose if I've got a text that says as dog was crossing the road and it was very tired. Let's consider this example. Now, if I've got an example text like this, what it says is, let's consider for the demonstration purpose, I'm processing the word that is called as the road. Okay, I'm processing the word that is my road. That is what I'm currently doing right now. Okay, I'm processing the word which is, so I'm processing the word that is road right now. So when I'm processing the word that is road, then here, while processing this current word of road, the words which are not important for me is this. Okay, so while processing this word of road, okay, maybe the information from the previous data, that is the word input, is not having any importance for me because the word the, okay, the word the is actually a kind of a filler word or a stop word, so I can ignore this. So this removal of the information from the word the is being done by the forget gate, and then by getting the input and processing this current input will be done by the input gate, where I'll get the current input, I'll add it to my long-term memory because dog is currently crossing the road. And if I want to generate the output at the current sequence, then I'll use my long-term memory as well as my current input, and I'll process the output from the output gate. So we will always have a long-term memory line that goes on, and this will remember the long-term dependencies that we have got on the text data. So this is the overall idea behind this LSTM neural network. Okay, so this is the overall idea, team. So with this LSTM neural network, so this has got wider implication and this has got wider application. This was used in various applications like Google search, learning the patterns in the data sets. All these things were being utilized, and we replaced the recurrent neural network with the LSTM neural network. So that was the great thing about this LSTM neural network. And more importantly, we started using this LSTM neural network in the complex task like sequence to sequence generation. So sequence to sequence generation is nothing but the many to many architecture. So in this many to many architecture, what we will have is we'll get multiple inputs and we will generate multiple outputs. That's the task where we wanted to focus more at that time, because this is one of the major challenge and this is one of the task where we want to progress more.
So the applications like machine translation were came into picture, and we started using this many-to-many architecture using the LSTM. So we started using it and we started seeing a lot of benefits over there. But we still had the challenge. Even though we were making use of LSTM neural network, we had the challenge of long-term dependencies. Even though the long-term dependencies were being captured when we talk about sequence to sequence generation, the long-term dependencies were still being a challenge, especially for this kind of task. So what researchers came up is, okay, they have analyzed the issues that we have got, and what researchers came up is, okay, instead of analyzing this sequence to sequence task directly with the help of encoder decoder architecture. So encoder decoder architecture is this. This is my encoder decoder architecture, which is a many to many architecture. So instead of uh, using directly, which you see right now, okay, so instead of using this encoder decoder architecture like this, let's have one more scenario that's called as an attention. And this gave rise to a research paper by the Google team, which is nothing but attention is all you need. So that's a research paper, and this changed the way that we looked into the task of this sequence to sequence processing. So we had a challenge with LSTM. Now we've got a solution, that is the attention mechanism. And this attention mechanism has been introduced from the research paper of attention is all you need. So I'll stop the video over here. In the next video, let's look into this research paper of this attention is all you need, and let's try to understand what is the benefit that this is bringing into the table and how it is beneficial for us when we are processing the long sequences. So we'll learn about it in the next video. Alright, now in this video, let's learn about the attention mechanism for the task of sequence to sequence learning. Now, when we talk about this attention mechanism, there's one research paper which you have to know that's called as attention is all you need. But before you go over there, that is the attention all you need research paper, there's a important concept that you need to understand that is the how does the attention would happen in case of the sequence based learning. So let's first understand the attention mechanism, and this attention mechanism is being explained in the research paper which is named as neural machine translation by jointly learning to align and translate. So if you look into the abstract, so the abstract clearly says neural machine translation is a recently proposed approach for machine translation. Here, unlike the traditional statistical machine translation, the neural machine translation aims at building a single neural network that can jointly tuned to maximize the translation performance. The models proposed recently for neural machine translation often being belong to the encoder decoder architecture, which is many to many architecture, and to encode a source text into a fixed length vector from which a decoder generates a translation. So in this paper, what they are trying to do is they are trying to use a fixed length vector. Okay, so this fixed length vector that we get, this would actually be termed as a bottleneck. That is what they are saying right now. The reason that we call it as a bottleneck, because if you look into the many-to-many architecture, this H2, whatever the output that I generate right here from this H2, this is the fixed length. Okay, this is of fixed length, and using this fixed length, I'm generating the output, which is the translation in the other language for the decoder. So this actually becomes a bottleneck, which means I am limited by the length of the output of this encoder, which has the responsibility to learn all the inputs. Hence, we call it as a bottleneck. Okay, so hence it is called as a bottleneck. So what they are trying to do is, as part of this research paper, they are proposing to extend this by allowing a model to automatically search for parts of a source sentence which are relevant for predicting the target word. Instead of limiting to the single vector, as part of this research paper, they have proposed so that we can get more information, and whenever we are generating the decoder, that is when we are trying to decode it,
At that time, we will pay attention to the words that we are interested in. Okay, with this approach, they were able to achieve the translation performance which are comparable to the existing state of the art phrase-based system on the task of English to French translation. So this is one of the important approach which gave rise to the transformers architecture. So this is very important that you understand this research paper at a very high level. So being this an advanced one, I'll try to simplify it as much as possible so that you will have the necessary insights from the research paper and you know what would happen in case of advanced transformer architecture. Now let's go through this scenario. See, when we talk about this encoder decoder architecture, so when we talk about this encoder decoder architecture, this will be a many to many architecture, and this will be composed of recurrent neural network, or it can be composed of LSTM neural network. Okay, it can be either composed of LSTM or RNN, and using it, we will be trying to perform the activity of encoder to decoder architecture. So if I want to represent this encoder decoder architecture, the way that I'll be doing right now is we'll consider this example, that is the encoder decoder architecture. So let's let's mention the steps. Okay, in case of my step one, okay, in case of my step one, so what I'll do is I'll be generating the input. So these are the two inputs that I've got. These are the three inputs that I've got. Coffee is good. So you are aware of the encoder. I'll just say step one of decoder. In the step one of decoder, I'm going to remove these parts. Okay. So I'll just keep a note of it. I'll copy this. Okay. And I'll mention and I'll keep multiple parts so that you will understand the how exactly the data is getting flown. Okay, so in the step one of decoding, so what we will have is we will have the output, that is H2. This H2 will be used in conjunction with this H2. So I'll be going ahead and generating the first output, that is cafe. So this is how I'll be performing the decoding. So I'm going to use this H2. Okay, I'll use this H2 over here. I'll represent it. Yeah, I'll use this H2. Using my H2, I'll go ahead and I'll generate the decoder. I'll be generating the first output from the decoder. So this will be my output from the decoder RNN, the first neuron from the decoder RNN. Okay, now once this is done, the step 2 of the decoder is something like this. So for the step 2 of the decoder, what we will do is, so here we'll still have the H2 over here. Using this H2, I'll be generating the next word, that is the cafeist. And my step 3 of decoder over here in this scenario, in the step 3 of my decoder, I'll be using my H2, and using my H2, I'll be generating the third word, that is cafeist good. Okay, so as you can clearly see, the entire dependency of generation of the output from the decoder is dependent on this H2. That is the last hidden state from my encoder. Hence, we call this as a bottleneck when we are performing the task of sequence to sequence training task. Now, what do we propose in the scenario of attention? So in the scenario of attention, the way that we are proposing is little different. So what we will do is, so I'll add a heading so that you'll be able to clearly understand what is happening in the scenario. Okay, I'll write it as with attention mechanism. So with attention mechanism, so the way that we would deal it right now is, so let's look into the step 1 of attention. So let's say step 1 of decoding. So in the step 1 of decoding, I'm interested in generating the output of this H3. I'm interested in generating the output of H3. Now, in order to generate the output of H3 and the first word, that is cafe, so what we will do is, so we will make use of all the previous hidden state. So it clearly means that, so here
When I'm generating the output of H3, I'll be using my H2, okay, and I'll use my H1 and I'll be using my H0. So instead of using 1, I'll be sending H0, okay, H1 and H2. So all these three data will be used as an input for my H3. Okay, based on these three inputs, I'll be generating the output. So let's say if I'm generating the decoder, if I'm generating the decoder as cafe, now cafe is actually for the word coffee. So that means in this scenario, the H0 will have the highest preference. To mention the highest preference, I'll just write it in a different color. So I'm using all three, H0, H1 and H2, but H1 will have the highest preference. So at this time, my decoder has the ability to refer to all the previous hidden states. Okay, this is a scenario for the step 1. Now in the scenario of my step 2, okay, in the scenario of the step 2 of my decoder, so what we will have is this time, so the second word is east. The second word is east. So for the second word east, the word that is important for me is east. So I'll be giving more attention. I'll be providing more attention on this H1 compared to H0 and H. So when I'm generating the step 2 of my decoder, at that time, I would still have the access to my all the previous hidden state and I can pay more attention to the word which is of my interest. In the same way, for generating the last output, that is for the generating the last output in this scenario that is good. So at that time, I'll be paying more attention to the word good compared to the other hidden state. So each time when I'm generating the output for my decoder, okay, each time when we are generating the output of this decoder, at that time we will have the choice to decide as where exactly that we want to pay the attention to. So in this scenario, while generating the output at the third state, I have the complete control as I want to pay more attention to the word good when I'm generating the output as good. So I want to give more importance for the word east if I'm generating the output as east. And I want to give more importance for the word coffee if I'm generating the output as cafe. So this is the overall idea behind this attention mechanism in a sequence learning technique. So that is what has been explained in this scenario as well. So this is the diagram that has been represented in the research paper. X1, X2, X3, X4 up to XT, these are all the input state, and H1, H2, H3, H4 up to HT, these are all my hidden states. Now YT minus 1 YT, so what it says is you can think of the above part as the decoder part. So when I'm generating the output for my decoder, I'll have an additional layer which is an activation layer which will help me to focus on the individual hidden layer parts. So for at each decoding step, I'll have the option to decide to which hidden state from the encoder that I want to pay more attention to. So this is the overall idea behind this attention mechanism in the sequence to sequence based model. And you can refer this research paper in detail. They have actually described how exactly that they were able to achieve. And at the end of this research paper, they have also mentioned how the attention is actually working. For example, for the word area, okay, for the word area, they are actually paying more attention to the la zone. Or when I'm generating the output as la zone as the translated word, I'll pay more attention to the word area. Okay, so ETE A, so for that I'll be paying more attention to the word was signed. So each time when I'm generating the output from the decoder, I'll be paying more attention to the specific parts. So this would help in overall remembering the data for the long sequences. So this is the core intuition behind this technique of the implementation of attention mechanism. I'll just come down and see whether we have any other important parts that I want to highlight. Yeah. So I think we have covered the important parts of this research paper. The key thing that you have to remember from this research paper for your advanced natural language processing is whenever we are decoding it, so the decoder will have the ability to pay more attention for the required parts from the encoder so that it can perform the decoding in a much more effective manner. So this is the overall idea about this encoder decoder architecture with attention mechanism. Okay, this is the core principle behind this attention mechanism. Now that you have understood this attention mechanism, there is one last bit about the transfer learning. So what exactly is this transfer learning and how this transfer learning actually helped us in the field of natural language processing, which gave rise to the building of transformers. So let's talk about the transfer learning approach in the next video. Okay, so till now you have learned some of the building blocks which led to the transformer architecture. Now in this video, we will look into the transfer learning technique which also made a clear impact when the transformer came into picture, and this also played a major role in improving the overall efficiency of the transformer architecture. So when we talk about the transfer learning, so transfer learning is a common way to train the deep learning model, especially for the task of computer vision. So the general practice that we follow in case of computer vision is, so suppose when we take the task as computer vision, let's assume it's a classifying the image data. So what we'll be doing in this scenario is using this pre-trained neural network like the ResNet. So we are going to adapt it for our given data set. We'll adapt it with our custom data. So that's the overall idea behind this transfer learning technique, and this is very common when we talk about the computer vision application. So by using this transfer learning approach, we are having a lot of advantages. So we are allowing the network to make use of the knowledge that has been learned from the original task. So when we talk about the architecture, when we are performing the transfer learning technique, so what we will do is, suppose if I've got a model, suppose if I have a model that would look like this. This is my deep learning model. So what I'll be doing is I'll be splitting this deep learning model into two parts. Okay, we'll split this deep learning model onto the two parts. Assuming that this is my deep learning model, I'll split into two parts. We call it as a head, and the other part we actually call it as the body. Okay, so this will be my body and this will be the head. So we will split the deep learning model into the two parts, that is head and body. Now the body will contains the weight parameters and the head contains the required output specific layer. Okay, so this is the overall idea. So during my training, the weights of my trained neural network will have the overall features. So this would actually contains the features and it has the overall learning from the given domain. To give you an example, suppose this is my deep learning model and this has been trained on an ImageNet data set. So when I have trained it on the ImageNet data set on this deep learning model, so this deep learning model has the complete features and it has learned the features, and in my output layer, I will have 1000 neurons, assuming that it's a multi-class classification with 1000 neurons. So this is the overall idea about this trained deep learning model. Now what I'll do is I'll split this trained deep learning model like the ResNet model, and we'll split it into two parts. Okay, and I'll split it into two parts, into body and head. Once I split the neural network into body and head, now what I'll do is, let's say I've got a new task. The new task is I want to classify cat or dog. I want to classify it as cats or dogs. So what I'll do is I'll make use of the body. Okay, I'll make use of the body. Now this body is made up of the parameters which has learned from the ImageNet dataset, that is from the domain of ImageNet dataset. Now I will have a different head. I will have a new head. For the demonstration purpose, I'll choose a different color. So I will have a different head, and using this different head, in this scenario, it's a binary classification. So as a result of this, I will have a single neuron. I'll have a single neuron, and I might add few dense layers which will enable my overall neural network to learn the patterns in the entire data set. So this approach is called as the transfer learning approach. So what we are doing in the scenario of this transfer learning approach is we are making use of the trained parameters on a specific domain. We are using the same as a starting point to perform the fine tuning on a new similar task. Now, by doing like this, we are able to train in a much faster way, and we are able to get the best result when we perform this task of transfer learning. So this is very much better compared to the traditional supervised learning approach. So in the overall computer vision scenario, as I mentioned, we'll be training a deep learning model on a large scale data set like the ImageNet data set, which would contain the millions of images. And we call this overall activity as a pre-training activity. Okay, we'll make use of this pre-training activity, and the main purpose of this pre-training activity is to teach the model the basic features of the images such as colors, edges, and so on. Then we will use these pre-trained models. We will get the body of the pre-trained model, and then we will fine tune it to the downstream task like classifying the image as whether it belongs to cat or dog. And these model that I have written right now, these models are called as fine-tuned models, and these fine-tuned models typically achieve higher accuracy than the traditional supervised machine learning models which are trained from the scratch. It could be machine learning model or it could be deep learning model as well, with the same amount of label data. Now, even though this kind of transfer learning approach became a standard approach in computer vision, for many years till now, this was not the scenario with natural language processing. So as a result of this, for each and every task, whenever we are building any NLP based application, we would require large amount of label data. Now, getting the large amount of label data was very difficult for us. Having the complexity of languages and the text data, preparing the label data set was very difficult. And also, whenever we were achieving the performance with large data due to the data issues and the computation issues, we were unable to proceed further and we were unable to reach the better accuracy on a large data set. Now, what happened was, in the year of 2017 and 2018, around those ages, various research groups proposed the various approaches that finally made the transfer learning possible for NLP as well. It started with an insight from the researchers at OpenAI. So what they have done was, the researchers at OpenAI, they obtained strong performance on sentiment classification by using the features which are extracted from unsupervised pre-training approach. So what they have done is they have performed the unsupervised pre-training. So in the transfer learning of NLP based task, so what we will have is we'll have a pre-training. So in this initial training objective, so what we'll be doing is we will take a very large corpus. Okay, we will consider a very large corpus, and by considering a very large corpus, we are going to perform a dummy task. Okay, what is the dummy task? The dummy task is, given the current word, what will be the next word? Okay, consider a large corpus, build a model or train a model on the large corpus, and this large corpus could be the Wikipedia data or the overall available text corpus that we have got with us. We'll build a model on this very large corpus with dummy task of, given a current word, what will be the next word? So this is the dummy task that we are interested in performing. And this approach is called as language modeling approach. So the best part is, when we want to perform this pre-training on the very large corpus, we don't have to find the text data. We don't have to require to get the large amount of label data. What we can do is we can just extract the data from various sources like choosing the Wikipedia site. And what we will do is we will split the entire data text corpus into the individual tokens, that is my individual words. And I would say, given my current word is 0, what will be the next word, that is word number 1. So this is called as pre-training. Now, once the pre-training has been performed, so next thing what we would do is we will perform the domain adaptation. So we will perform the domain adaptation. Now in this domain adaptation, what we will do is on the required task at hand, we will perform the fit on the domain data. Okay, we'll perform the fit on the domain data. For example, so once I have performed the pre-training on a very large general corpus, I'll just go ahead and perform the similar activity on the domain that I'm interested in. So it could be the IMDb data if I'm working on movie, and it could be the research data if I'm working on scientific research based model. So in this way, we'll perform the domain adaptation. So this is my step 2. So the step 1 is pre-training, which is also known as language modeling, and the step 2 is actually my domain adaptation. And then we will have the third step, which is what we call it as a fine tuning. So in this final step of fine tuning, what we will do is we will make use of the trained language model which has obtained the domain adaptation. What we will do is we will add a classification layer, assuming that it is a task of classification. So I'm going to add a classification layer at the final layer, which will help me to perform the required task. That means we will take care of task at hand. Okay, we will perform the task at hand in the scenario of this fine-tuning approach. So this is the core approach, and this core approach resulted in the best models that is possible with the help of natural language data. So by introducing this pre-training, domain adaptation and fine-tuning, we were able to get the higher accuracies on the very complex tasks like sequence classification and the sequence generation, which was actually a bottleneck in the pre-era of transformers. So with the attention as well as in combination of the transfer learning, we were able to achieve the higher accuracies in the advanced language models. And one such model which actually changed the way that we looked into the NLP field is the transformer model. So let's understand what exactly is this transformer model, and we will look into this transformer model at a very high level, and then we will look into its implementation in the further section. So I'll see you next time. All right, so welcome back to your learning journey team. So you now have the overall idea about what has actually led to the transformer and the key concepts that you need to be aware when you have to learn about the transformer. Now, if you're seeing this transformer architecture for the first time, don't worry. So it might look complicated, but it's very simple. It looks little complicated if you're seeing for the first time, but it's a very simple one. And when it comes to implementation, it is easy to implement as well. So I'll try to decode you and I'll try to simplify this so that you will have a high level details as what is happening in this scenario. Now, in this transformer architecture, we will have two things. We will have an encoder, and along with that, we'll also have something called as a decoder. The left hand side that you see right now is called as an encoder. The right hand part that you see right now is called as a decoder. So let's understand this from bottom. So first we have got the inputs. So here the inputs are nothing but the text data. Suppose if I have a text that says as dog is walking. Okay, so my inputs are nothing but my individual words, which is my string. Since I cannot use the string representation as it is, what we will do is we will have an embedding representation, that is a vector representation of the individual words. Okay, we'll just have a vector representation of the individual words. Now, one key thing that we were doing in case of recurrent neural network is we were actually passing the data in a sequential manner. So if I bring back our concept, see in the scenario of this encoder decoder architecture, sending each and every feature at a single time. Okay, so at which means I had to process the first data, and only once my first data, that is first word, has been processed, then only I was able to process the next word. So this was the challenge of this encoder decoder architecture, that is with LSTM or RNN. So what researchers have decided is, okay, let's do one thing, let's include the parallelization since we'll be making use of GPU. So what they have mentioned is, so we'll be sending all these three words together. Now what we will do is, on top of this, to represent its position by intuitively saying that this is my first word, this is my second word, and this is my third word. To intuitively represent those position, they represented with the help of positional encoding, which is nothing but the sinusoidal function. So it's a sinusoidal function which will help us to represent the individual word positions. Now by representing my individual word position, so we are able to process all the three words together. Now then we will enter an encoder. This is an encoder structure. Okay, this box that you see right here, this is nothing but a single encoder. Now in this single encoder, I have got the multi-head attention. So multi-head attention is nothing but, it's very similar to the attention that we have learned. The only difference is I will have multiple such attentions. Okay, I'll have multiple such attention. Just think of it in that way for simplification. And then we will have some normalization layer. So this will help us to learn the data in an effective manner. And we also have some connections, residual connections. So this will help us to overall learn from the data set in a much effective way. And this is followed by a simple feed forward layer. Now this feed forward layer will just get the data and process it, and then we will also have some residual connection, and we will have some normalization layer. Okay, so this completes my encoder. Now when it comes to the decoder, so when we are doing the decoding, we will be sending the token as well as our previous output as well if it is a decoding. So what we will do, we will send that output from the encoder to the multi-head attention. Along with that, we will also send something in the output layer, that is for the input for the decoder, somewhere right here. We will shift one step towards right. This is to ensure that my future words are not visible. We will do a positional encoding. We will have some masking to ensure that my future words are not visible to me. We will have some normalization layer and the recurrent connection, that the residual connection, followed by the multi-head attention feed forward, and at the end we will have a linear layer with the softmax activation function. So with this combination of encoder decoder architecture, where it has got the multi-head attention and the positional encoding, we are able to achieve greater accuracy when it comes to the text data. So what they have done is, they have used these kinds of architecture, build the language models, and once they have built the language models, we were able to use that language models, fine tune it for the given task, and we were able to achieve greater accuracy with amazing speed when it comes to generating the prediction. So that's the importance of transformers in the NLP world. Okay, I hope you have now understood the importance of transformer and how it connects together with the various concepts of deep learning. So with this, we come to the end of this video. In the next video, we will be starting a new section which is about how to work with Hugging Face library and how Hugging Face library plays an important role in the natural language processing related task. So I'll see you next time. As you know, the transformers are changing the way that we are processing the NLP data. In this video, let's have a high level understanding about the components of the transformer that will help you to get a deeper understanding at a later point. So this is a very high level understanding about transformer, and these are all the building blocks whenever you are starting your learning journey in this natural language processing. So this is a very basic representation of the transformer architecture. Now in the transformer architecture,
This has been clearly created for the task of neural machine translation. Now, what exactly is this neural machine translation? It's a task where I'll input in my language A and I'll get the output in my language B. That is what a neural machine translation is all about. You can take an example of Google Translate. So when you say Google Translate, you'll input you'll input in one language and you'll get the output in another language. That's what the task is, neural machine translation. Now, why is it important? Now, the reason this task is very important, especially in the world of natural language processing, is previously, prior to transformer architecture, we were making use of RNN or LSTM in order to work with these kind of architecture, and we were creating an encoder decoder architecture. Whatever the data that I'll get from the user, I'll process the data through a specific set of layers. We call it as an encoder layers. And this encoded data will be moved to my decoder. So input, encoder, whatever the output that I'll get from the encoder, let's say I'll call it as context. This is the compressed representation of all the input data. And I was using this context as an input for my decoder, and the decoder was generating the output in another language. So this was the encoder decoder architecture before the transformers. And then researchers have come up with the advanced functionalities, and what they have decided is, instead of simply using a single context, why don't we include an attention? That's when the attention came into picture. The research paper, attention is all you need, that's what it talked about. It said how the attention adding to the context will help us in improving the overall accuracy of the model. Now, along with this attention, what had happened in the NLP area was, so the researchers came up with the another technique, that's the transfer learning technique. They came up with the ULM fit, which is a framework or an approach which introduced the transfer learning approach to the natural language processing as well, because at that time the transfer learning was mainly a mainstream in the computer vision. And ULM fit paper told us that the transfer learning can be extended to the natural language data as well. Now, with the combination of attention and the transfer learning approaches, this this overall idea or this concept of transformers take took a steep turn. I mean, like this actually gave rise to the it will not be wrong if I say that these two are the key things for the transformers. Now, with the concept of attention and the transfer learning, the overall transformer architecture came into picture. Here, in my encoder, in this transformer architecture, we also have the encoder decoder architecture. Now, what we'll have is, first I'll have an input data, and this input data will be sent to my input embedding, where I'll be generating the compressed representation of my text data with the help of word embeddings. Now, the best part in this scenario of transformers is I can send all the input together to ensure that we are specifying in a correct sequence, because that's what the language is all about. We are going to send the data to our positional encoding. The output from this positional encoding will be sent to my multi-head attention. So this will help the model to learn the dependencies from one data to the other terms that I've got in my sequence. And here I'll be using the multi-head, hence we call it as a multi-head attention. At this point, we call it as a self-attention. The reason is I'll be learning the relationship between my current words to the other words in my sequence by itself. That means by looking into the data itself, the sequence itself. Hence it's called as self-attention. And it moves to the add and normalization layer, followed by feed-forward network layer and add and normalize layer. Now, coming to the right hand side part, this is my decoder part. In this decoder, here we've got the data. So whatever the data that passes through the decoder, I'll first send it through embedding, which is the compressed vectorized representation of the text data. We are going to add the position details. This gets passed through the multi-head attention, add normalization layer. Then followed by multi-head attention, feed forward layer network, and so on. Here, this attention is called as mask attention, and this is the
cross attention. You can clearly see we've got three types of attention: self, mask, and cross attention. So this is the overall architecture of the transformers. We'll get the data, we'll pass through to the input embedding, we'll add the position details, we'll send it through the multi-head attention, which is going to learn the relationship between other words in the sequence, pass through the feed-forward network, and once the encoder stack is complete, we will have the context. And using that context as well as the mask details, I'll have a cross attention layer, and this is the masked attention layer. So once the data passes through encoder decoder architecture, the encoder finally gives me the output in terms of probability, that is with the softmax activation. So this is the overall high level architecture details about the transformer architecture. So team, if you want to learn more, please let me know in the comment section. I'll be happy to take you through the in-depth explanation about the transformer architecture in the further videos. So thank you so much for watching, and I'll see you next time. So in this video, let's understand about the Hugging Face library and its importance in the NLP world. See, when we talk about working with any advanced architecture like the transformer architecture, so there's a lot of things that has to be done and that has to be taken care when we are implementing such kind of complex architecture. So when we talk about the overall research, okay, when we talk about the overall research and the researcher, whenever he submits the paper, so what he or she will do is he or she will implement the code in PyTorch or the TensorFlow. They might use the PyTorch or TensorFlow, which they are currently using it for research, and then they will implement the overall architecture. Okay, they will be implementing this overall architecture in this PyTorch or TensorFlow. Now, once they have actually implemented it, okay, they have trained it at their end as well. So they will perform the implementation, okay, and then they will have to save the model weights. Okay, they'll have to save the model weights, and then once the researcher has actually created those kind of architecture, maybe in PyTorch or TensorFlow, and he has saved the weights, now think about it from the practitioner. If I'm building those kind of architecture, then as a data scientist, so as a data scientist, I also have to do the same thing. So what I'll have to do is I'll have to implement the architecture in this with the help of PyTorch or TensorFlow. And then once I build it with the help of PyTorch or TensorFlow, I'll have to load the weights. Now, once I load the weights, I'll have to pre-process the input data. And once I perform the pre-processing of the input data, then I'll have to implement the data loader, and I'll have to ensure that I'll have to define the custom loss function which they have defined in the research paper. And then I also have to ensure that the learning algorithm also has to be implemented. So as a data scientist, I have to do all these things just like a researcher has done it. So even though I'm interested in using that model, so if I have to implement any kind of complex kind of architecture, I have to take care of all these things from my end itself. Now the challenge is the research person or the person who has submitted the research paper. So he or she might have implemented in a different architecture itself. For example, he has implemented in a framework called MXNet, and he has saved the weights with the help of the MX weights. When that would happen, now imagine as a data scientist, if you're trying to implement it in TensorFlow, you will have to do another research from your end in order to ensure that you are able to load that model and get those model weights in order to get the complete benefit of the pre-trained model which has been trained by a research group. So this was one of the main challenge that we had when so many people started introducing the complex model architecture. And that's where the transformers came into picture. So when we talk about this transformers, that is the Hugging Face transformers library. So what they have done is they have actually provided a standardized interface to a wide range of transformer models. And not just that, they provided the code support
for variety of model frameworks. It could be JAX, or it could be PyTorch, or it could be TensorFlow. So they started supporting all these libraries by default. So as a practitioner, I can just decide what is the transformer model that I have to use. Okay, and I can mention what is the framework that I have to use, and I can load the models including the pre-trained weights. And it doesn't end there. So this overall Hugging Face library, that is the Hugging Face transformer, so they actually started providing the task specific head as well. That means if I want to make use of a specific transformer model architecture and which has been trained on a language model, I can decide, okay, I want to use this language model for performing the task of classification. So I can actually have my own task specific head so that we can fine tune the transformers and get the benefit of the same. So as a result of this, this has helped us in reducing the time for us to code and reducing the time in creation of NLP projects from months together to just weeks right now. So this is the advantage of this Hugging Face library. Now you can learn more from this documentation page. This is the home page. So here they say that it's an AI community building the future, where you can build, train, and deploy the state-of-the-art models powered by the reference open source in machine learning. And there are a lot of organizations who are using the Hugging Face, and it's a home for machine learning. We've got the amazing documentation provided by this Hugging Face team, and we'll be using the same as we progress in the learning journey. And you can get to know about the company. So the overall machine and the overall idea of this Hugging Face company is to democratize the good machine learning one commit at a time. So that's the overall agenda of this company, and you'll be seeing a lot as you progress in the learning journey in this section. So I hope you are excited to learn about this Hugging Face library and how you can make use of transformers. So let's get started from the next video. I'll see you next time. So in this video, we will look into the various tasks that we can perform using the transformer architecture with the help of Hugging Face library. So whenever we talk about any natural language processing task, it just starts with a piece of text, that is a text data. So here I've got a text review on a specific anime show. So it says Code Geass is one of the series that everybody recommends, and once you watch it, you know why. So it just mentions each and everything, and it is a review. Okay, it's just the overall review that that I have actually scraped from a website. Okay, so let's consider this text as an example test, and on this text data we will go ahead and apply the various natural language processing tasks. So that's the overall idea right now. Now we'll just see what are the things that we can do. So in order to apply this transformers, first I'm going to install the transformers right now. Okay, so I'll just go ahead and install the transformers. And once I install this transformers library, so I'll also install the data sets. Okay, which is also a module which is present inside this Hugging Face library. And I'll install the sentence piece, which is very important for me. You'll see everything in action as you progress in this coming learning journey. So once this is installed, we'll just go ahead and start importing the various libraries as part of our requirement. I'll start by importing my data sets. I'll import Hugging Face Hub. Then I'm going to import Matplotlib library as well. And then I'm going to import the transformers. Okay, this will take care of all the necessary imports. Now, once I do the import, so we have already decided what is the text that we have got. So it's asking me to restart the runtime. Let me just do that so that we can effectively work with the same. I'll just re-execute the code from top once I've restarted the runtime. Okay, now once we have that data ready, so the first task that we are going to see is text classification. So text classification, as you know, it's a classification task where given a text document, I want to classify the text document into one of the predefined classes. That's the overall idea about this text classification. And when we talk about this working with this Hugging Face Transformers library, so this Hugging Face Transformers library has a layered API which will allow us to interact with the library at various levels of abstraction as part of our requirement. Now, one of the common way that we work with is with the help of pipeline. Now, this pipeline is going to abstract away all the steps that is required for us to convert the raw text into the set of predictions from a fine-tuned model that we have got. Now, while working with this Hugging Face transformers, we'll generally start by instantiating the pipeline. So in order to instantiate a pipeline, we'll make use of a pipeline function. So first thing is, let's import the pipeline function from transformers. I'm going to import the pipeline. So once I import this pipeline, I'll initialize or I'll instantiate my pipeline with this pipeline function. I'm going to write it like this. I'll say classifier is equal to pipeline. Okay. And inside the parenthesis, I'll have to specify the task that I want to perform. Now in this scenario, I want to perform the task of text classification. Okay, so in this way, we will specify the task and this is going to instantiate a pipeline for us. Now, when you're executing this cell for the first time, so you will see that some things will start downloading. Here it says it is downloading some language model, and what it will do is it will also download the model weights. So all the necessary things which is required for us to perform the task of classification automatically, it will be downloaded by default. Okay, so it will be downloaded by default. Now when we are executing at a later point, it will make use of cached version. So this is what the pipeline is. So I have now downloaded the model. Now what we can do is we can generate the prediction. Now whenever we define a pipeline, this pipeline gets the string of text. It could be the list of strings as well if I've got multiple text document, and we can send those string as an input, and this pipeline is going to return us the list of predictions. Now whenever it would generate the prediction in the format of the Python dictionary. So let's go ahead and apply the classifier pipeline on our text data. If I apply this classifier pipeline on my text that we have defined earlier, if I execute this, this would result in a Python dictionary. Here it says the label is positive and the score is 0.9979. So what it means is my model is confident that the given text data that I have got belongs to the positive sentiment. And it clearly makes sense because it's a positive review of an anime series. Okay, we are dealing with the positive review of an anime series and the label clearly says it's a positive sentiment. Okay, and I've got the score closer to 1. Okay, so I've got the score closer to 1, which means it is 99.79% confident that this given text data belongs to the positive sentiment. So this is how we interpret the outcome from the classifier pipeline. Now when you're dealing with the multiple data, so the general practice that we do is we will convert the output into the pandas data frame so that we can display the output in a structured manner. So I'm going to write it like this: out is equal to classifier, and I'll specify the text, and then I'll just convert this out into the data frame. So this will describe the output in the format of a data frame. Okay, so that's how simple it is to perform the task of text classification with the help of Hugging Face library. Now, similarly, let's go ahead and perform the task of NER, that is named entity recognition. So you are aware of it already, how complex the named entity recognition is. Now let's see how we can perform this activity of named entity recognition. So when we say named entity recognition, we are interested in classifying my individual words to one of the known classes. That's the overall idea right now. So I'll call it as NER, and here instead of text classification, this time the task is named entity recognition, that is NER. And I'm going to mention my aggregation strategy. I'll specify my aggregation strategy as simple. That's the strategy that I'm going to use right now. Okay, I just have to specify this task inside my pipeline. Next, I'm going to write it as out is equal to NER, and I'll apply my text data. Next, I'll just generate a data frame from this output. So if I execute this will download the required language model. And once it downloads, so my model will be applied on the text document, and we'll be able to display the output in the format of a data frame. So this will tell us what is the individual entity that I have got. So I'll have an entity tag for individual words. Then we'll also have the confidence score next to it. Okay, that's the overall idea right now. So let's wait for the result. All right, so what we were able to see is, I think for the first text that we had, that is the text review, so we were unable to identify any classes over there. It also makes sense because that is based on the anime review, hence we could not see much of the named entity tag. So what I have done was I have taken our general text. So I mentioned as Narendra Modi is a Prime Minister of India. Now, when I applied it on the NER model, that is the pipeline that I had created for this task of named entity recognition, so we are able to generate the output. So person and the location, the word, the start and the end, and the respective confidence score. Okay, so this is the overall idea behind this named entity recognition task. So as you can clearly see, it's very easy for us to understand what is happening and what is the entity group it would belong to. Here PR means the person, LOC means location. So in this way, we can get to know the entity group. And not just that, while working, okay, while working, let's say if I'm building the question answer based system. So that means if I'm interested in the task like question answering, then we can also create a pipeline as well. So here, the next task that I'm interested is question answering. So for the demonstration purpose, I'm going to write it like this. I'll say reader is equal to pipeline, and here the task is question answering. Okay, next I'm going to mention the question. The question is, what does user says? Okay, I'm just asking the question as what does user says from the text data. This is the question that I want to answer. So I'm going to say it as outputs is equal to reader, question is equal to question. Okay, and context is the text data. And finally, I'm going to generate a data frame from this outputs. And if I execute this, so this is going to download the language model, and then it will help me to answer the question. So here I'm saying as what does the user say? I'm asking about what does the user is actually speaking about. Okay, the user is actually speaking about code Gs. See, and we also, and since it's a complete review data, we don't have much of the confidence, but you can understand what does the user says right now. Now instead, if I say what does the user want, okay, so let's see what is the output that we get. The user want is, so user says one of the best animes ever made, and that is having 0.39. That's pretty much close from the given text data. And remember, I'm just using the model out of the box. I'm just using the model out of the box. Okay, and let's say if I'm interested in the task like the summarization. So if you remember, in the previous learning journey, we have performed the text summarization using NLTK module. Now here I can directly perform the summarization by creating the pipeline as summarization. I'll show you. I'll say summarizer is equal to pipeline. The task that I want to perform is summarization. Okay, and this time I'm going to mention it as output is equal to summarizer, and I can mention my text. Okay, along with text we can also mention some condition. Let's say clean up tokenization spaces is equal to true, and I'll also specify the maximum length, okay, as 90. Okay, this is what I would specify. Then I'm going to say print. I'll generate the outputs, which is from the 0, okay, 0th index, and I'm interested in getting the summary text. Okay, this is what I'm interested to extract. So here we are loading the model. So we've got the output. Here the output says the only aspect I see as a flaw is the art. With 9 out of 10, the people seem to be little bit deformed or too skinny. So it has by far the best story I've ever seen. You'll just get hooked into it from the second episode. See, what it has done is it has summarized the overall text review that have got with me, and I was just able to use the model out of the box. That's it loaded the pre-trained model, and out of the box it has created the summary, and this summary is pretty good. It is able to perform the summarization in a much better way, capturing the important information. Okay, now here I have made use of the parameters like the maximum length and the cleanup tokenization pipelines. So by using this, I was able to tweak the outputs at the runtime. Okay, now let me show you one more interesting feature. So I can also perform the task of machine translation. So let's say I'm interested in converting the language, let's say from text review in the English language into the different language. I can also do that. To show you the same, I'll create a pipeline. Okay, this time the task is translation. So here from English to, let's say, DE, that is German. Okay, I'll specify the model name. The model name that I'll be using is Helsinki NLP slash opus MT ENDE. This is the model that I'll be using right now for performing the task of text classification, text translation, that is machine translation. I'm going to mention like this: output is equal to translate, and here I'll specify the text, and I'll also mention the cleanup tokenization spaces, and I'll also specify the minimum length. Okay, I'll also specify the minimum length. Now once this is done, I'm going to generate the output. I'll say output, and I'll get the 0, and I'll get the translated text. Okay, if I execute this, this will generate the translation from English to DE. Okay, now let me open the Google Translate. Now let's go ahead and perform the translation and see how it would look like. Okay, it is recommending something over here. It is recommending to install the sacred. Okay, so let's wait. So it's actually translation text. So I modified from translated text to the translation text. So let's wait for the output. Okay, so we have got the output right now. So it says code G is in, and it is mentioned in the German. So let's do one thing. Let's copy everything. Now using this output, if I perform the Google translation, see, I have just pasted the text over here. It says Code Geass is one of those series that recommends everyone, and once you watch it, you'll know why. See, everything that you have seen in the original text, it has been translated successfully to the German, and I'm able to convert it back to the English. So that's the best part from the default model that we have got right now. It's pretty much good. It has produced a very good translation for us. And we can also perform the task like text generation as well. So if I want to perform the text generation, okay, I can also perform the text generation using the text generation pipeline. You can check out the text generation pipeline at your end and see how exactly the text generation is going to work. This text generation mainly has the applications in chatbot and all those kinds of application. Okay, so from this, you have understood the power of Hugging Face library. Now, when we talk about this Hugging Face library, so this library, like we generally call it as an ecosystem.
And this ecosystem is generally present as the Hugging Face hub. So if I draw this box and if I call this as an Hugging Face hub, okay, so this is my Hugging Face hub. So in the Hugging Face hub, we have got the family of libraries, and we also have the hub as well. So here in this Hugging Face hub, we have the models. Okay, we have the models. Let me use a different color. We have something called as models. Okay, and we have the data set. So we have models, we have data set, and we also have the metrics which will help us to measure the performance of the NLP task. Okay, and then we also have what we call it as a documentation. This is what my Hugging Face hub is made up of. Okay, so apart from this Hugging Face hub, in this Hugging Face ecosystem, we also have the code. Okay, we also have the code as well. Now when I talk about the code part of this Hugging Face, okay, if I call this as code part, Hugging Face, so we will have kind of a tokenizer. Okay, we will have the what we call it as a transformers. Okay, so all these part of my coding hub or the code part. Okay, which will be part of my code part. So this is the overview of this Hugging Face architecture. You can check out the official documentation page for more information, but this is the core aspect of this Hugging Face ecosystem. Now when we say Hugging Face hub, so if I take you to the home page, so this is basically the Hugging Face hub that you see right now. Okay, you've got models, you've got data set, we've got documentation, we've got spaces. Okay, and there's a lot of sections that you have. You can use the same. We've got metrics. So all these things are available right now. Okay, and the best part is the pre-trained model. You can use the pre-trained model. Okay, and using this pre-trained model, we can actually test and evaluate the model from the high level itself using this Hugging Face hub. So this is the overall idea about the Hugging Face library and working with Hugging Face hub. All right guys, so with this, we come to the end of this video. In the next video, we will see how to perform the text classification using this Hugging Face library using the pre-trained models. So we'll see how we can load the model and how to work with this Hugging Face library in the next video.
So in the last video, we have converted the integer representation of the label into a string format using the custom function, that is the label to str, that is the label to string. Now let's go ahead and look into the frequency of classes in a given data set. So this will help us to understand what is the composition of the data, whether we have the data which is a balanced one or whether we have the data which is an imbalanced one. Now in order to create that visualization, so let's go ahead and import the necessary module. So this time I'm going to import matplotlib.pyplot as plt. Okay, now once I import this module of pyplot, next I'll just go ahead and create a visualization. So this time for creation of visualization, I'm going to access the column of label name. Okay, and I'm going to mention the value counts function, and inside the parenthesis I'll mention it as ascending as true. Then for this I'm going to call the bar plot, which is a horizontal bar plot. Okay, so the column name is labels name. For that labels name, I'm performing the value counts. So this will return me by saying it as what is the frequency of occurring. And using those values, I'm creating a bar chart. Then I'm going to add a title that says as frequency of classes. Then I'll say plt.show. We'll execute this cell. So this will help me to visualize the overall frequency of this given data set. So we can see that this given data set, that is the emotion data set that we are using it for performing the text classification, is a highly imbalanced one. So we can observe that the joy and the sadness, so these two classes appear frequently in this given data set. And if you look into the below two, that is love and surprise, they are actually very rare when it comes to this availability, or when it comes to this occurrence of these class names. And if you look into those values here, this is close to 500 or something, and this is more than 5000, which means surprise is 10 times lower than the joy, and love is close to 5 times lower than the joy. That is what we would observe with this given frequency of this data. Now, in this scenario, what can we do it? Well, if you are in a typical machine learning scenario, obviously we'll have to first fix this imbalance. So we'll have to perform the oversampling, or at least we'll have to go for undersampling, or we'll have to try getting more examples for the underrepresented data set. That is the underrepresented classes. So those are the three strategies that is generally recommended when we are dealing with this imbalanced data. Now, since we are working to understand how to perform the classification, let's go ahead and keep this unbalanced data as it is, and then we'll just go ahead and continue with the analysis of this data set. Now, another important thing whenever we are working is understanding what is the maximum length, what is the length of the data set, or the length of the document, specifically speaking. The reason this length is important, because when we are representing the text data into a numerical format, the length, understanding the length, that is the maximum occurrence length, will help us to build a perspective as what should be the context size. Because each and every model, like the transformer model, it expects the maximum context size. Now, if I have any values which is greater than the context size that I have got, then in such scenarios, there is a chances of truncation. Hence, it is very important that we need to understand how many number of words that I have got in my individual text document. So what I'm going to do is, I'm going to create a new column. So I'll write it as words per tweet. Okay, so here I'll select the column of text. I'll perform the split on the basis of space. Okay, then what I'm going to do is, on top of this, I'll just apply the basic function of length. So once I perform this split on the basis of spaces, I'll apply the len function on the resulting data, and whatever the outcome that I'll get, I'm going to save it inside a new column of words per tweet.
Next, let's create the box plot on this panda series. So I'm going to say df words per tweet box plot. Okay, so let's go ahead and try to visualize the same. So I'll just execute this. So currently it is I'll have to convert it to string and then split. Okay, so we'll have to call the box plot on the data frame df.boxplot. Here I'll mention the column name of the words per tweet. Okay, I'll keep it like this. Okay, so I have mentioned df.boxplot, specified the column name of words per tweet by label name. Okay, so here this is how the overall plot would look like. I'll switch off the grid by writing it as grid is equal to false, and we can also add the x-axis and the labels if we would require. I'm going to write it like this. I'll say plt dot so the title. Okay, and I'll just mention it as blank. Okay, so this is how the overall visualization would look like. So the maximum number of words per tweet that I would observe is greater than 60. So that is what I would observe in this given data set. And the median value is between 15 to 20. That's the overall median value that I would observe for individual labels that I have got in this given data set. Okay, now just for your understanding, the maximum context size that my transformer model, like the model like the distill BERT, which can handle is 512. So the context size that I've got in my test, that is in my training and the test data, is pretty less than 512, which means there is no chances of truncation. We will not be losing any crucial information from the text data set. Okay, so now that we are satisfied with the analysis, if I want to get back the data into the format of dataset object, so I'll say emotion. Okay, so I'll say emotion and then I'll say reset format, emotion dataset dot reset format. So this will reset the format. So then we can just go ahead and start working with this dataset object. All right. So what we have done right now is we have performed the preliminary analysis on this text data. Now, in order to work with this text data and perform the activity of classification, I cannot just use this raw data as it is. I'll have to split this raw text into the individual tokens, and that is where the process of tokenization come into picture. Now, one of the general way that we can perform the tokenization is performing the word tokenization. But let me just take you through the steps as what is the core principle behind it, and then we'll talk about the same. See, when we talk about this tokenization, okay, so here we have various types of tokenization. One is character tokenization. Now, when I say character tokenization, so what I'll be doing in the scenario is I will encode each and every character that I have got in my text data into a numerical format, and then I'll be representing those text data into a numerical format. So that's called as a character level tokenization. See, when we are using this character tokenization, what it happens is, as you have studied in the earlier sections of this NLP journey, the structure in the text, the structure in the text will be ignored. And the whole string, the entire string or the entire document that I'll be dealing with, it will be termed as a stream of characters. Now, when we are working with this character level tokenization, this will definitely help us in dealing with misspellings in the data set or even the rare words as well. But the problem is when we are understanding the text data, we are unable to understand the linguistic structures like the words that has to be learned from the data. And this is one of the major drawback of character level tokenization. And that's one of the major reasons that we do not generally see the usage of character level tokenization. So what we do is, apart from this character tokenization, we have another method that's called as a word tokenization. Now in the scenario of this word tokenization, here we will split the document into the individual words. And these individual words, we will be mapping them to each of the integer. Now while doing this, since I am keeping the words together, as a result of this, I am able to learn the linguistic structures in the given data set. But the problem is, each and every unique word in my document will be treated as my individual unique word in my vocabulary. So if I have a very large vocabulary, then at that time I will be requiring more number of parameters when I'm training my deep learning neural network. Now just think about this. Suppose if I have 1 million unique words, then in such scenarios, imagine the number of parameters that you need to have in the first hidden layer if it contains 100 neurons. So at that time, definitely this is going to result in the low performing model, and we don't want to be in that position. So what is the goal for us is, we need a goal. So the idea is, have a kind of a tokenization which will help us to balance out the benefit of character tokenization as well as word tokenization. So that's the goal right now. So goal or the requirement is, find a way to efficiently perform the tokenization. So here what researchers have proposed is, when we talk about the transformer architecture, they have proposed the use of subword tokenization. The process is subword tokenization. So the core idea behind the subword tokenization is to combine the best aspects of both character tokenization and the word tokenization. So what we want to do is, whenever we come across a new word, that is the word that I have not come across, I'll have to be able to deal with those new words in an efficient manner. So that's where the character tokenization was actually good at. On the other hand, we want to keep the frequent words and perform the aspect of word tokenization. So this is one of the main feature of this subword tokenization. So what it is going to do is, it is going to learn everything from the pre-trained corpus. Whatever the corpus that I'll have, I'll learn all these tokenization. Okay, that is the words and the subwords and everything. And from there, I will try to interpret it in a better way. Now, while working in the research world, that is in the NLP space, there are various subword tokenization that are available. Now, one of the commonly used subword tokenization is the word piece. Okay, word piece is the commonly used subword tokenization, and that is what is used by BERT and the Dialogflow tokenizer. So let's go ahead and see how to perform this subword tokenization. In order to understand the same, so what I'm going to do is, I'll make use of auto tokenizer. So auto tokenizer is a class that will help us to load the tokenizer which is associated with the pre-trained model. The reason that we use this because each and every model, when it is trained by a researcher, he or she might have used the individual tokenizer. So when you select a model, each model will have its own tokenizer. To help us load the correct tokenizer for the model that we would specify, we will make use of this auto tokenizer class. First, I'll start by importing the same. From transformers, I'm going to import auto tokenizer. Here, I'll specify the model. So the model that we are going to use for this activity is Dialogflow base uncased. This is the model that we'll be using. Okay, now what I'm going to do is, in order to load my tokenizer, I'll write it as auto tokenizer dot from pre-trained, and I'll mention the model name, that is my model checkpoint. So this auto tokenizer class that I'm trying to load, this belongs to the larger set of auto classes. The main job is to automatically retrieve the model configuration, pre-trained weights, as well as the vocabulary from the name of the model that we would specify. So by doing this, this will help us to quickly switch between the models. And if I want to download a specific class as well, I can also do that. So that's the level of the ability that is given by this Hugging Face team for us. Now let's see how does this tokenization will be performed on an example text data. So I'm going to mention the example text data like this. Okay, I'll just execute this. This is going to load the tokenizer relevant for this model, that is distill BERT. Okay, so I'll get the text data that look like this. I'll say my favorite food is masala dosa. Okay, this is my text corpus that I'm going to have. Now what I'm going to do is I'm going to generate the encoded text. I'll generate the encoded text by sending the text inside my tokenizer. Okay, finally, I'm going to print this encoded text. So if I print this encoded text, so this tokenizer is going to result in two values. It will result in input IDs. Along with that, we also have the output that says as the attention mask. So what has been done is this has processed the text data, and after it has processed this text data, it has performed the subword tokenization. And after the performance of this subword tokenization, so I have actually represented the integer representation of the subword tokenization. So let's do one thing. Let's see how does this tokenization has been performed for this text data. In order to understand how the split has happened for this given text document, we've got a method that's called as convert IDs to tokens. So I just have to mention these input IDs. So I'll write it like this. I'll say tokens is equal to tokenizer dot convert ID to tokens. Okay, and inside the parenthesis, I'll just have to mention my encoded text. So this encoded text is in the format of a Python dictionary, or a kind of a Python dictionary. So more specifically speaking, so this is in the format of encoding. So I can just mention this batch encoding object and get the attribute of input IDs. And if I execute this, and then I'll also print the tokens, that will be easier for us to visualize. So this will tell us how my document has performed the activity of tokenization. So my is one token, favorite is one token, food is another token, then MAS is one token, and then we have got ALA, that's another token, DOS is one token, A is one token, and apart from that there are two more special tokens that has been added, that is CLS and SCP. So these two tokens, CLS and SCP, they are specially added because that is one of the expectation from the model that has been loaded, that is distill BERT model. Okay, and these special tokens might be differing for model to model. Now that's the beautiful part about this Hugging Face. So I can just mention the model that I have got. Okay, using the model that I have got, so if I send that tokenizer, so my text will be processed such a way that as per the requirement of the model, the tokenization will be performed. And here there is something called as // or the hash. So hash means this is not exactly the individual word, so it is the continuation of the previous word. So in this example, the word masala, the masala word was not present in my vocabulary. So what it has done is it has split into two subwords as per the vocabulary that this model has been like good with. So in the model vocabulary there are two words, MAS and ALA. So I have split the entire word of masala into two different tokens. So this is the beautiful part about this subword tokenization. So here this prefix double hash, it means that the preceding string is not a white space. Okay, that's the overall idea right now. Now, if I want to understand how exactly the string would look like, there's also a special function that's called as convert tokens to string. So I can say tokenizer dot convert tokens to string, and inside the parenthesis I can mention my tokens. So if I execute this, see, this has resulted in bringing back the original text. It says my favorite food is masala dosa, and I have a special tokens that is CLS and SCP. Okay, so this is how we can apply the tokenization for the given text data. We just have to initialize our tokenizer, specify the model, and we can just send in our text data, and this will apply the tokenizer as per the required model configuration. We also can see the special tokens as well, CLS and SCP, as per the model requirement. Okay, and this CLS index value is 101, and SCP, the integer representation, is 102, and the my representation is 2026. So in this way it is going to represent the each and every word that I've got in my vocabulary of this tokenizer into the integer format. Now if I want to understand what is the length of my vocabulary, then I can just call the attribute that's called as vocab underscore size. So this will help me to display the size of my vocabulary. It says 30522, so that's the size of my vocabulary. And if I want to understand what is the model's maximum context size, that means what is the maximum size or the maximum size of tokens it can accept in a single document. So I can call it like this. I'll say tokenizer dot model max length. This will return us the model's maximum length. Here it says 512. So this is the length of my document that I can have as a maximum. If I've got more than 512 words in a given text document, the after 512, whatever the words that are present, it will be truncated. So that's the importance of this model maximum length. And whenever we are working with the model expects two important parameters. They are input IDs and the attention mask. And you can check what is the expectation from the model by calling the model input names. So I can call it as tokenizer dot model underscore input names. So this will return us the model input names. I've got input IDs and the attention mask. Okay, so these are the names of the fields that the model expects in the forward pass. So now that you have the basic understanding of this tokenization process for a given single document, let's apply this tokenization on the entire data set, that is our emotions data set. Now while performing the tokenization, we have to perform the tokenization on the entire data set, that is on my both training data as well as test data. So we'll stop the video over here. Let's continue in the next video where we will learn how to perform the tokenization on the entire data set. Okay, in the last video you have seen how to apply the tokenization on a text document. Now moving ahead in the learning journey, let's apply the tokenization on the data set, that is our entire data set. So here, one thing that you always have to remember, that whenever you are applying the tokenization, especially by making use of pre-trained model, it is very important that you make use of the same tokenizer that the model was originally trained with. So from the model's perspective, what you will be doing is, if you switch the tokenizer, it's like shuffling the vocabulary. It's like giving the examination on mathematics for the learner who has been trained on the physics. So does it make sense in real life? It does not, isn't it? If you're a physics student, if you're given to solve the mathematics paper, it will be difficult for you and you'll perform poorly. The same thing will happen whenever we are applying the tokenization. So it is very important that you make use of the auto tokenizer class and mention the model that you're going to use to load the correct tokenizer for the data that you're working with, and that would be the same tokenizer that you will be using it on the model. Okay, now coming to the tokenization on the entire data set. Here in order to tokenize the entire text corpus that we have been given with, there's a function that is called as map function. So using this map function for our dataset dictionary object, so we can go ahead and create new rows and the columns for the given dataset. Now I'll show you as how it actually works. So in order to do this activity, the first thing that we have to do is, so we need a pre-processing function which will help us to tokenize our examples. So in order to tokenize the data set, I'm going to write a function called tokenization, and this will get the batch of the data set. Okay, for each and every batch of the data that I would get, what I'll do is I'm going to apply the tokenizer on this batch of the data. So the batch of the data that I'm interested to perform is text. Okay, for the text column, I want to apply the tokenizer. Now, while applying the tokenization, once that is done, I will say padding is equal to true. Now, why this is important? So think about it from the model perspective. So whenever we are working with machine learning or a deep learning model, we would expect that each and every row in my data set has equal number of columns. The same thing is true for the transformer model architecture itself. So let's consider a scenario. I've got multiple rows in my data set. I've got row 1, and here this contains 16 words. Okay, and I've got row 2, and let's consider 20 words. Okay, now this is the individual words that I've got. So if I try to visually represent it, assuming that this actually represents 16 words. Okay, this is the vector which represents 16 words. Okay, then if I want to represent the 20 words, obviously this will be bigger than 16 words. Maybe this is the size of the vector, which is of the length 20. This will be 20 words. But if you think about it from the model perspective, we have to ensure that each and every row will have the equal number of length, will have the same length before we send it for our model. Now, another key aspect is this time it's a pre-trained model scenario. It's a pre-trained model scenario. That means my model has been already trained on a specified number of input units. Now, in this scenario, my input size is actually 512. So 512 is the length of my input size for this given data set, because that's the length of my context. So I'll just say 512, which is my model's context. So what I have to do is, whenever I have the 16 words, I'll have to ensure that even though it could be 16 words, I have to extend it. Okay, I'll have to extend it such that it will become overall, it will become the 512. Okay, I'll just expand it for demonstration purpose. These are the dummy values. So normally this will be equal to 0, and this time for the first example, this will be of the length 496. Okay, this will be of the length 496. And for the second row, I will be adding the dummy values, and this dummy values will be of the length, so 492. So in total, if you observe, after adding these dummy values, the total length of my input, okay, total length of my input will become 512. So 496 plus 16 is 512. 492 plus 20 is 512. So these red values that you see right now, these red values are called as the padded values. So these are the padded values which has been initialized to 0 such that we add it at the end of the given data, that is at the end of my words, such that the total length will match my model's context size. So in order to do this activity during the creation, that is during the writing of the program, I have mentioned as padding as true. This is one of the important parameter that we have to mention. And then I'll also say truncation as true. Okay, so let me just give you an idea about the truncation. So let's say, okay, I'll consider an example. I'll consider the example where my row 3, okay, my row 3 is having 520 words. Okay, my row 3 will have the 520 words. So when I have the row 3 of 520 words, I'll just mention my row 3 like this. Okay, so assuming that this length represents my 520 words. Now, when I say truncation, what it means is, I'll show you with an example with the visualization itself. What I will do is, this is the 520 words of the row. When I say truncation, so I'm going to reduce the words, okay? I'll reduce the words in my input data such that it will become 512 words. The difference value that you see right now, okay, the difference values, these will be the truncated values. Okay, I'll just give you an example. So this time they are actually the truncated values. These are the truncated values that I have got on this data set. Okay, so truncated values are nothing but these will be ignored. So these text will be ignored. So what I'm saying is, in this given example, if you come across any sentence which is greater than 512, truncate those values. 512 is the hard limit. Now in this scenario, we don't have to worry about it because the maximum length of my given text document, that is my individual text document, is well within the context size. So we don't have to worry about it, but that's the meaning of this parameter, that is truncation and padding. So to help you recap, so padding will help me to extend the length of my individual document to match the model context size. Truncation will also help me with the model context size, but it will help me to reduce the number such that it matches the model context size, in this scenario 512. So this is the overall idea behind the working of this tokenization. Then what I'm going to do is to give you a demonstration. So I'm going to call the tokenization function on top of this emotions. Here I'll select the training data set and I'll just send in first two rows. Okay, I'll just send in first two rows for performing the tokenization. So once I send that, we'll be able to see the outcome. So if you observe my input IDs here, so let's look into the shape of this. If you just go ahead and look into the shape, so 101, 1045, 2134, 2102, 2514. So what it has done is, by default, when it does that, okay, by default when it does that, it is going to perform the tokenization such that, since I have not mentioned the maximum context size, it is going to refer to the maximum context size from the given text corpus itself. Okay, so this would refer to the models with the maximum context size itself, and based on that, it has found that 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23. It has decided that the maximum context size for this example will be 23. Okay, so based on that, it has performed the tokenization, and you can observe in the scenario, see, so for the second row, I've got the complete 23 entries, and for the first row, since it was less than 23, there is a zero padding over here. And to represent, these are all the dummy values. If you look into the attention mask over here, see, if you look into the attention mask, I have mentioned as 0. So this attention mask will help the model to say that, hey, these are all the dummy values. You can just go ahead and ignore it. So that is how we would go ahead and apply the tokenization. Now, once we have defined this pre-processing function for tokenization, if you want to apply it on the entire data set that we have created, what we can do is we can go ahead and make use of the function that is called as map function, and inside the map function we'll specify the tokenization, okay, which is the function that we have created, I'll say batched is equal to true, and I can specify the batch size. I'll just say it as none so that the batch size can be determined automatically. Now once I execute this, okay, and if I then go ahead and display my emotions data set, okay, if I go ahead and do this, okay, this is resulting in the output. So it is adding two new columns, input IDs and the attention mask, after it applies the tokenization. Let's do one thing. Let's save it in a variable. I'll write it as emotions encoded and I'll display the same. So what this is going to do is this will apply the tokenization on my emotion data set, and whatever the outcome that I'm getting, I'm saving inside this input IDs and the attention mask. These are the two new columns that I'm adding right now. Okay, so with this, we have completed the activity of applying the tokenization on my given data set. All right, so with this, I'll stop the video over here. Now, as we proceed in the next video, we will see how we can train the text classifier on this given data set. So I'll see you next time. In this video, let's go ahead and perform the activity of classification. Now here, in order to perform the classification, in this current scenario, we'll be making use of BERT model. So this is the model that we'll be using it for performing the classification. So what does this BERT model is made up of? See, this BERT model is made up of the encoders and decoder. So what we will have is we'll have an encoder decoder architecture, as you are aware of it already. So this also follows the encoder decoder stack. Okay, now what we will have is we'll have a text data. I'll just mention it like this. We'll have a text data, and from this text data we will perform the tokenization. This is the box that would represent the tokenization. Okay, tokenization. Okay, so this box would represent the tokenization that we perform on the text data. Now once I perform the tokenization, what we will do is we are going to have the embeddings of the model. So once we generate the embeddings of the model, then the data would pass through my encoder stack, the decoder stack, and this is the overall structure of this BERT architecture. Now, apart from this encoder decoder architecture, in this scenario, we are interested in performing the activity of classification, which means in this scenario, okay, in this scenario, we are interested in having our own separate head, which we call it as a classification head. We need to have a classification head so that we can perform the activity of classification. So that's another point that we need to consider right now. Here we want to use this classification head, and using this classification head, so we want to perform the task of classification, and at the end we want to generate the prediction. So this is the overall model architecture that we are trying to look at. This encoder decoder that I have mentioned right now, this together we call it as an transformer model architecture. I can call it as a transformer model architecture. Okay, this is my transformer model architecture which is represented in this box. So this is the current idea or the current architecture that we are trying to understand right now. Now this box that I have represented, you can visualize this as a BERT model. Okay, let's assume that this is a BERT model that I have got. So this will be my BERT model. Okay, this is the BERT model that I want to perform it for the classification. So in order to implement these kind of tasks, okay, we've got various approach. One approach is called as a feature extraction approach. So that is called as a feature extraction approach. So what happens in the scenario of this feature extraction approach? So in this feature extraction approach, what we will do is we will get the pre-trained model. So this BERT model will be a pre-trained model. Okay, now the data that I'll get, the new data that I'll get the new data, I'll pass through this BERT model, and I'm going to generate the output. So this would generate the output, which are nothing but the features from the pre-trained model. Okay, so the features that are extracted from the feature pre-trained model, on top of this, what I can do is I'll use these features and I'll apply it on the machine learning model, and using the machine learning model I'll perform the training and I'll be generating the predictions. Okay, we'll generate the predictions from the pre-trained model. This is called as the first approach, that is the feature extraction approach. So that is approach 1, feature extraction approach. So I'll have the text data, we'll perform the tokenization, the embeddings will be getting it, and then we'll pass through the encoder decoder architecture, that is a pre-trained model. And once we have got the features, so we will train the machine learning model and we'll be generating the prediction. Now in this scenario, okay, in this scenario, that is this part, that is extraction of the model, sending the data, all these things, this overall pre-trained model that you see right now. So the thing that you have to remember is this will be a fixed one. Okay, this will be a fixed one. So what does it mean by a fixed one? So it would mean that here there is no model parameter, so we will freeze the model. We'll just freeze the model in this scenario. So once we freeze the model, whatever the output that I'll get, that is the feature, and this machine learning model will have the ability to learn or ability to update the parameters. So this is the first approach that we'll be doing right now. So I'll use this pre-trained model and I'll pass the test data and I'll generate the features, I'll extract those features, and then on the extracted features, we will apply the machine learning model. So this is the first approach that we are going to perform right now. So let's go ahead and implement this first approach. So in order to do this, let's use the pre-trained model. So I'll start by loading. So I'll say from transformers, import TF auto model. Then we have already decided the model that we have got. Okay, so I'll say transformer model. So I'll do it one thing, I'll say model name is equal to the model that we have created earlier. Okay, this is going to get the model name, or it's better that we specify the model name specifically, Dialogflow base uncased. Okay, then I'll create a model instantiation. So I'll say TF auto model dot from underscore pre-trained, and inside the parenthesis I'll mention my model name. So here I'm making use of this auto model class. So this auto model class is from the Hugging Face transformers library. Now using this method of from pre-trained, we can actually load the weights of a pre-trained model, which means I'm loading the weights of this pre-trained model of Dialogflow. Okay, that's the overall right now. So once I execute this, this will download the model weights. Now once it loads the model weights, okay, then we can go ahead and perform this activity of extracting the features. So remember, TF auto model, yes, TF auto model is the model class that we use it for TensorFlow. Now in case if you're trying to load the PyTorch model, then you can make use of this auto model class. So that's the main difference of loading the TensorFlow model or a PyTorch model. That's the main difference, team. Now if I want to perform the forward pass on this given data set, so first thing that I'll have to do is I'll have to apply the tokenizer. Now when we are applying the tokenizer, if I want to return the data which are in the format of TensorFlow tensors, then I just have to say it as return under TF. I'll show you how it looks like so that you'll get a better understanding of this. So example text is equal to, this is a test document. Okay, next I'm going to write it like this. I'll say inputs is equal to tokenizer, and inside the parenthesis we can specify the example text that we have got, and here On top of this, in case if I want to specifically return it as a TensorFlow 1 version, I can say it as TF. So this will return the output in the format of the TensorFlow tensor. So if I print the inputs, okay, so you'll be able to see the overall tensors. See, this is of the tensor of the type tf.tensor. So this is how we can return the output as a tensor. Okay, now that's how we can go ahead and perform this activity. Now once I have the input, so if I want to apply on top of my model, that means if I want to perform the forward pass, I can just send in these inputs into my model, and then I can just display the outputs. So this is going to generate the output for me. See, the output that has generated is TF model output, okay, and this is of the shape 1, 6, 768. That means my output is of the shape 768. In total, I have got 6 tokens. For each of the token, I am representing the individual output, that is the output from my decoder is of the shape 768. So that is how I'm generating the output for each word. Remember, for each word, I'm getting the output of the vector of the shape 768. Okay. Now, what we'll be doing is as a practice. So in order to perform the feature extraction, we'll be extracting the first feature that I've got in my given data set. I'll just extract the first feature, that is the token of 101, the initial feature that I've got, and I'll use that feature in order to build my model. So let's go ahead and do the same. So here, in order to perform the extraction from this model, so what I'll do is I'm going to create a function that's called as extract hidden states. Okay, now this will consider a batch of the data. Next, what I'll do is I'm going to get the data set, and while sending the data, so when I'm sending the batch, okay, I'll be actually sending the complete 4 columns in my data set. So if you look into our data that we have got, so in this scenario of this emotions encoded, when I'm performing and when I'm trying to perform the forward pass, I'm going to send all the 4 columns. But I'm actually interested in getting only the data which is expected from the model, that is input IDs and the attention mask. I should not be using text and label whenever I'm performing the forward pass. So in order to do that, I'm going to construct the output. The way that I'll be constructing the output is for k comma v in batch.item. See, this is like a dictionary, isn't it? So when I call the items, this is going to return key and values. I'm going to check if the key is present in tokenizer dot model underscore input underscore names. So you know already what exactly is this tokenizer underscore tokenizer dot model input names is going to return. So this tokenizer dot model dot input names, it's going to return what is the expectation of the model. So in this scenario, the expectation from the model is input IDs and the attention mask. So if the key is present in that model names, then only I'll keep it. So I'll say k, so then only I'll keep those values as an input. I'll consider it as my input. Then in order to extract the last hidden state, I'm going to write it like this. I'll say last hidden state is equal to model, and I'll apply my inputs over here. Okay, then in order to extract the last hidden state, I'll say last hidden state. That means the final hidden state is what I'll be getting it. And then what I'll be returning is, I'll be returning it like this. I'll say hidden state, that is my features. And here I'll extract the last hidden state. And from this last hidden state, I'll be interested in saving only the first index value, that is the feature values for the first index position. Okay, this is how I have written this function, that is extract hidden state. Now this emotions that we are working, that is this emotions encoded that we have created, so This data set is in a general data set format. So we are working with the TensorFlow model. Since we are working with the TensorFlow model, we have to ensure that we set the format of this data in the format of a TensorFlow tensors. So I'll say set format TensorFlow, and the columns that I want to ensure that it should be in the format of TensorFlow is input IDs, that is important for me, and attention mask, this is important for me, and the label that I've got, even I'll be converting it into the TensorFlow tensors. Okay, input IDs, attention mask, and label, I want to convert it into the TensorFlow tensors. I'm not converting the text because anyways this will be taken care, and we already have the tokenization which takes care of the same. So our tokenizer is having the ability, okay, it will have the ability to convert the data into the tensor format. Okay, I don't have to worry about it. So I've set the format like this. Once I've set the format, so we are now good to apply this function. So now if you look into this emotions encoded, see we have got the same data set object. I have mentioned all these things. Now the only thing that I want to do, if I want to hidden data, so if I want to apply this function is, I'll say emotions encoded dot map, and here I'll say extract hidden states, that's the function, and I'll say batched is equal to true. Okay, so the code has been executed. So we have performed the forward pass, and once we perform the forward pass, we have actually stored the hidden data, that is the final hidden data was there, right? So with that hidden data, we have created this variable, that is emotions hidden data. So that is what we have done till now. So what exactly is this? So this is actually my features. This will be my features. I'll use these features as my feature matrix, and then we will go ahead and perform this activity of classification. So let's go ahead and do that. So using this given data set, let's go ahead and generate the feature matrix, that is my X and Y. So I'm going to say prepare the data with features extracted. Now, how do we prepare the data? So the way we prepare the data is, I'll start by importing by NumPy library, and then here I'm going to mention it like this. I'll say xtrain is equal to np.array, and here I'll say emotions. What is the output? Emotions hidden data. Then from here I'll extract the train, and the specific thing that I'm interested in extracting is hidden state. Okay, I want to extract the hidden state from the training data. That will be my xtrain, and I want to do the same thing on the validation data as well, or array emotions hidden data. Here instead of train, it is the validation data. Then we will go ahead and perform the activity of extracting the ytrain as well. Ytrain is equal to emotions hidden data. Here np.array emotions hidden, I'll say train, and instead of hidden state, this would be the label. Okay, so I'll copy this and I'll paste it again. So finally this will be the y valid. Okay, so np.emotions hidden data, I'll say validation, and then we will specify the label. Now once this is done, I'll just display the shape of my xtrain as well as our xvalid. So this will help us to display the feature shapes that we have got. My input is of the shape 16,768. So if you remember, I had 16,000 rows in my data. That means 16,000 rows in my training data. So for each training data, I have converted into a numerical format by performing the forward pass. So I have performed the forward pass and I have extracted the features. In the features that has been extracted, I have selected only 768 features for the first special token that we had got. Okay, and I'm using these 768 features to apply the machine, to apply it on the machine learning model. That's the overall activity that we are going to do. Now, let's go ahead and try to visualize the given data set. In order to visualize the given data set, I'm going to install the library that's called as UMAP Learn. So UMAP is nothing but Uniform Manifold Approximation and Projection for Dimension Reduction. This will help me to just go ahead and help me reduce the number of dimensions from 768 to, let's say, 2 dimension, and then it will help me to create an overall visualization. In order to do this activity, I'll just specify the code that would look like this. Here from UMAP, I'm importing the UMAP function, and I'm also importing the min-max scalar, application of the min-max scalar. Then here I'm specifying the UMAP with number of components as 2, and I'm performing the fit on the X scaled, which is the scaled version on my training data. Then we will just go ahead and display the data. So I've created a data frame with 2 features, X and Y, and the respective label. Now we'll just try to visualize this given data set. Now in this given data set, there are actually total of 6 labels that we have got, that is 6 expression of labels. So let's try to visualize how does the overall plot would look like if we try to visualize the given data set. Okay, so let's see. So I have performed the dimensional reduction, and this is a code which will help me to create a plot. See, this is just a projection of 2 dimensions. Okay, we have compressed the 768 dimension into just 2 dimension, that is a low dimension space, and we are trying to understand how does the overall labels and the features would look like. So from this scenario, we can observe a specific pattern. The negative emotions like anger and fear and sadness, if you look into this scenario at a very high level, the Higgs-Bean plot looks very much similar. And the same is true for happy as well. Like love and joy, they are having the similar data distribution. So that's what we observe in this scenario. All right. So it's not so much so clear because we are trying to compress the data, but overall this is the pattern that we observe. So here the machine learning model that I'll be using is the logistic regression. So I'll start by importing the same from sklearn.linear_model. I'm going to import logistic regression. Here, this is the logistic regression model. So what it means is I'm using the features which I have extracted from the pre-trained model, and using those features, I'm training on the machine learning model. So here, the ML model is the logistic regression model. So I'll initialize my logistic regression model, and here we'll specify the max iter as 3000. Okay, then we will go ahead and perform the fit lr.fit xtrain comma ytrain. Okay, and once I perform the fit, we can go ahead and calculate the, let's do one thing, let's calculate the accuracy score. So x valid comma y valid, let's go ahead and calculate the accuracy score. So this will help us to understand what is the overall accuracy that we are getting if we are using the pre-trained model as a starting point, if you are using the pre-trained model and using the pre-trained model as a feature extractor. So let's wait for it to execute. So by the time the execution gets completed, so to compare how does the overall model would work, let me do one thing. Let me also import a dummy classifier. So this will help me to get a overall idea about the baseline. Okay, I'm going to import the dummy classifier. Okay, and here I'm going to write it like this: dummy classifier and strategy is equal to most frequent. So I'll perform the fit on this dummy classifier. So now this will help us to validate what is the performance from the dummy model, that is the model which will just predict the most frequent class every time, and the logistic regression model, that is the machine learning model that we have fit. So from this output we can see that we are getting the accuracy of 63.35%, and if you look into the dummy classifier, we are getting the accuracy of 35%. So Here, the dummy classifier, that is the most frequent class, is 35%, and the model output that we are getting from the logistic regression model approach is 63.35%, which is better than what we have got from the baseline classifier. Now, if we go ahead and plot the confusion matrix, this is the overall output of this confusion matrix. So it is performing really well in this confusion matrix. And one thing that we could observe is, so anger, and let's look into the other class where exactly it is getting confused. Yeah, anger is getting misconfused with sadness. That is what we would observe. Okay, and fear is also getting confused with joy sometimes. Okay, so sadness, okay, is performing well. So we can understand from this overall confusion matrix as how exactly the models are getting confused. Okay, the love is getting confused with joy. So that is the overall pattern that we observe in this given data set. All right, so what we have done is in this scenario, so we have performed the task of classification and we have implemented the first approach, that is the feature extraction approach. So with this, we'll stop the video over here. So we'll continue further in the next video where we will look into the next approach, that is fine-tuning approach. So see you next time. So in this video, let's talk about the fine-tuning approach. Now, when we talk about this fine-tuning approach, what we will have is, so we will not have the freezing the model. So what I'll do is, I'll make use of the complete model that we have got. Okay, I'll make use of the complete model, that is the Dilbert model. On top of this, what I'm going to do is, I'm going to have a classification head. So we will have a classification head, and in order to ensure that we are able to perform the fine tuning on this given data, so what we will do is we will perform the activity of tuning. Okay, we'll perform the activity of fine tuning for very less number of epochs. So that is what I'll do. So at the end of my trained model, that is the model that I've got, that is a Dilbert, I'm going to add my classification head. So using my classification head, I'll perform the prediction. That is the overall activity. Now, while during the training, so when we say fine tuning, we'll just fit on few number of epochs, maybe less than 10. Okay, so this will help me to perform the fine tuning for the task at hand, that is for the given data set. So that's the second approach that we are going to perform right now. Now, in order to perform the pre-training, so if I want to load a specific model directly for the scenario of classification, that means the pre-trained model with the head, okay, so we can make use of the TF auto model class. More specifically, this time we can make use of a class that's called as TF auto model for sequence classification. Okay, so that's the next activity that we will perform. So from transformers, I'm going to import my TF auto model for sequence classification. Okay, here I'm going to initialize my number of labels that I've got in my data set as 6, and I'll specify my model as TF auto model for classification. Okay, and inside the parenthesis, so yeah, from here, from this class, I'll call the function called pre-trained, and here I'll mention my model name. Okay, and the number of labels is the number of labels that I've mentioned. So num labels is equal to num labels. Okay, this will load my model, that is the model that I want, Dilbert model, with the sequence classification head. That means I'll have a classification head. Now, what I'm going to do is, in order to perform the training, so we have already loaded the model. Let me do one thing. I'll call this specifically as TF underscore model because it's a TensorFlow model. Now, what I'll be doing right now is whatever the column names that I'll have, I'll just convert into the TensorFlow tensors. I think we have done already, but let's just ensure that I'm doing it correctly. So tokenizer dot model input names. Okay. Next, I'm going to say TF train dataset is equal to emotions encoded, and here I'll get the training data. So I'll say 2 underscore TF data set. Okay. Now what I'm going to specify is I'm interested in columns is equal to tokenizer columns, and label columns is equal to label, and we'll also say shuffle is equal to true. Okay, and we'll repeat the same thing for the TensorFlow test data as well. Okay, so I'll say validation. Okay, so we will get everything and we'll perform the shuffle. All right, so this will help me to get the data in the format of TensorFlow tensors. So, okay, batch size, that is also important, 128. So since it is fine tuning, we'll just go ahead and run it for only few number of epochs. So first thing, I'll start with import. So from TensorFlow dot keras dot optimizers, I'm going to import the Atom, and from TensorFlow dot keras dot losses, I'm going to import sparse categorical cross entropy. Okay, from TensorFlow dot metrics, I'm going to import sparse categorical accuracy. Okay, so next we'll just go ahead and compile the model. So tf model dot compile, and here, okay, I'll mention my Atom. So learning rate is equal to 0.5. Okay, this is what I'll specify it as learning rate, and loss is equal to sparse categorical cross entropy loss, and then matrix is equal to sparse categorical accuracy. Okay, so this is how I'll be specifying everything. Okay, loss is sparse categorical cross entropy. I'll say from logits is equal to true, and matrix is equal to sparse categorical accuracy. Okay, next we'll just go ahead and perform the fit. So I'll say tf train dataset, then validation data is equal to tf test dataset. And since it is fine tuning, I'll mention the number of epochs as 2. So this will go ahead and perform the fine tuning. Now once this is done, we'll just go ahead and perform the prediction. I'll say tf underscore model dot predict, and let's go ahead and perform it on the test data itself, tf test dataset. Okay, so this is going to generate the prediction. Now if I just call the logits dot shape, okay, so this will generate the shape of the output. Okay, now this will generate the shape of the output. Now from this output you can also go ahead and compute the metrics as per your requirement. Okay, so we have the output results right now. So this is the overall output that look like this. Now if I apply the evaluate function on the test data, we are seeing this sparse categorical accuracy of closer to 93.65%. So this is what we observe on this given data set. All right, guys. So with this, we come to the end of this video and the end of this section. So I hope you guys have enjoyed and understood how to work with this Hugging Face library and how to work with the same and perform it in an efficient manner. That means how to perform the fine tuning as well as feature engineering and the classification. So that is what we have learned as part of this section. So thank you so much for watching, and I look forward to seeing you in the next section. In the next section, we will understand what exactly is this ChatGPT and how it works at a very high level so that you can proceed in your learning journey and use it for your future purpose. So I'll see you next time. Welcome back to your learning journey. Now in this video, let's learn about the ChatGPT. So what exactly is this ChatGPT? See, this ChatGPT was actually launched by OpenAI on December 1st. So this ChatGPT is actually a chat interface. It's a chat interface that has been trained, and this has been trained. The overall idea is it has been trained to act as an assistant. Okay, so basically, if I want to give you an in-depth idea, so this specific chat GPT that you have seen and you have seen all in the news is it's actually a language model. Okay, we have got a language model. On top of this language model, they have built a chat interface. So they have built a chat interface on top of this language model, and this has been trained to act as an assistant, answer the questions, and as well as perform wide range of tasks. Now, in order to get started, so you just have to create an account at OpenAI website and you can get the access to this model for free. Now, because of a lot of users accessing it, they have actually stopped the signing up in their website, but you can just join the wait list and you'll be getting the access very shortly. Now, one cool thing that you have to note down from the numbers perspective is just 5 days after the launch, there are already millions of users who have been testing it there and they are actually sharing the result. You might have observed that in the news and in the websites and the LinkedIn, everyone is sharing the results of the chat GPT. So let's understand what exactly is this model, and let's look at some of the most interesting result that this model has actually produced. So the motivation behind this OpenAI ChatGPT is, so the GPT-3, which was an earlier one, it actually missed the user's intent. So the GPT-3 was unable to understand the context that was actually there whenever the user was performing the what we say the interaction with the bot. And another motivation is they wanted to find that get a more quality out of the model of the same size instead of going a bigger model, which means they were actually trying to find a better model with the same model. That means get the better result from the same model instead of getting the bigger model. That's the main intuition and the main motivation behind creation of this chat GPT. Now, when you look into the overall model architecture and the ChatGPT details, so this model architecture of this ChatGPT, it has used the GPT 3.5 as a base. Now, this GPT 3.5 actually refers to GPT-3, and this has been trained through Instruct GPT. It's another model that we have got, and this GPT-3 has been trained through this Instruct GPT. And the setup of this chat GPT is very similar to the setup of Instruct GPT, which was released in the previous year. Essentially, the approach that has been employed is it uses the human labeled and the human produced data. This is very important. It uses the human labeled and the human produced data, and using this human labeled and the human produced data, the model is then fine tuned on the desirable chart logs which are created by the human beings itself. Then on top of that, we have performed the reinforcement learning in order to optimize the previously trained fine-tuned model. So the Instruct GPT is based on the supervised learning. The first part is usage of human labeled plus human produced data. Using this, we will perform the supervised machine learning. Then there is a reinforcement learning where it is going to use the desirable chat log, and using this desirable chat log we are going to perform the reinforcement learning. That's the overall intuition behind the training of this architecture. So the step one is regular fine tuning, where the human AI trainers, they are provided with the conversations in which they played both the side, the user as well as an assistant. Now once this data has been created, this data is then used to fine tune the model. Okay, this is the step one. And the step two of this model architecture is create a reward model for reinforcement learning. So in order to do that, we actually require to collect the comparison data. So we wanted to get the comparison data. So what we did is, so like this actually consisted of two or more model responses which are ranked by the quality. Now to collect this data, we took the conversations that the AI trainers had with the chatbot, and then they randomly selected the model written message, sampled several alternative completions were created, and AI trainers have actually ranked it. And once that is done, the humans compare the answers and choose what they like the best. So that's the step two. And what this has done is this creates a reward model, which is a small version of GPT that takes in the prompt and the multiple generated answers as the input and predicts which answer the human will prefer. So overall, this is built using the RLHF system. So the reinforcement learning algorithm, if I want to represent this, I'll have an RL algorithm. Okay. Now this RL algorithm is going to perform some observation about my environment. Okay. On the basis of the observation, it is going to take an action, and this will be applied on the environment, and this will be sent for my reward predictor. Okay. This is another small ChatGPT model, and using my human feedback, okay, we will be generating this predicted reward. So this will be a predicted reward. So here the reinforcement learning that occasionally will ask a human observer to choose between the few different generated outcome, and the overall idea is whenever it comes across the environment has the observation, when the action is performed, so next to understand to get the feedback signal, so it goes to the reward prediction, and then the human input it will take, and based on that we are going to predict the overall reward. So this is the overall idea of this step 2, that is the reinforcement learning activity. Then the step 3 is about the fine tuning. So in the fine tuning step of the step 3, the reward model will act as a human labeler, and we feed in prompts to the GPT-3, and then we are going to receive an answer. And then after that, the reward model is used to score the prompt and the answer paired. And this score is used as the feedback for the GPT. And this is overall controlled by the reinforcement learning algorithm. And this algorithm is actually called as PPO algorithm as per the research paper and the documentation released by the ChatGPT. Okay, so PPO is nothing but proximal policy optimization. So this will be the step 3. And here, when we talk about this context size, so context window, actually the OpenAI didn't release about the context window. So when someone has actually tested it, so we were able to find that it can take closely 16 medium sized paragraph. Like you can think about the context window size of 8192 tokens. That is what most of the people who have experimented with this chat GPT-3 have actually shared the data with us. Okay, and then coming to the user count, like as I mentioned, there's millions of users started using this overall chat GPT-3. So that's one key thing that we need to remember. Just 5 days after the launch, so 1 million, more than 1 million users started actually using this. And when we talk about ChatGPT-3, it's very important that you understand that the competitor of this ChatGPT-3, that is Google. So we have got Google as a competitor, and this Google, they also have a model that's called as actually Lambda. You might have come across if you have been in this NLP space. So this Google's Lambda is actually better than the ChatGPT. But the problem is they're not planning to release it. So there are a variety of reasons. The reasons for not releasing the Google Lambda, because the Google Lambda is very much costly to deploy, and in order to have a large inference, so they need to have a large inference cost as well. So that's another scenario that we have got, and they are more worried about the liabilities about what models say. And also they are much more worried about the accuracy of the result and what happens when the Google returns wrong result. So these are some of the challenges that the Google has, and Google do not want people what looks like an authoritative answer. That would be very wrong, isn't it? So people will have a tendency that if my lambda gives an answer, it will be an correct answer, but in reality it could be a wrong answer as well. And also the business model of Google is not in line with the same as the ChatGPT, hence they are not so sure of releasing it to the public yet. Okay, so that's one of the key thing that you need to remember. So this what GPT can do is this GPT can act as a substitute for Google search as per the various experiments conducted by various users. And this GPT-3 can actually help us in identifying the security vulnerabilities. This GPT-3 can refuse nonsense requests as well. So here, when we talk about the general models of natural language processing, it was just generating the outcome. So we can also ensure that with the feature that we have got in ChatGPT 3, it can refuse nonsense request as well, and it can write these stories collaboratively. These were some of the various things which users were able to do, and I've documented it and I'm sharing it with you, team. And the ChatGPT 3 can ask clarifying questions as well whenever you are performing the chat. And then this ChatGPT 3 can write a game of tic-tac-toe. Okay, and this ChatGPT 3 can write the music, and we have seen users doing the homework and write an essay as well. So with the help of ChatGPT 3, and we have got some users who are able to write a script to scrape the website itself, and they were able to create a script, and they were able to ask the ChatGPT 3 to explain the regular expression. And like these were some of the key things which we were able to see the advantages and the amazing features that the users were able to perform with the help of ChatGPT 3. And these are just a small list, and if you dive deep into this research domain, you can see there are multiple applications people are actually trying out. But this is not complete without specifying about the limitations. So as identified by OpenAI, so ChatGPT sometimes writes plausible sounding but incorrect or nonsensical answers. So that's one of the key things that we have observed, and this has been reported by few users as well. Now, the reason that this could happen because during the reinforcement learning, there is no source of truth. And this is one of the major reason as why this is very difficult to fix it. And training the model to be more cautious causes it to decline questions that it can that cannot answer it correctly. And supervised learning sometimes misleads the model because the ideal answer depends on what the model knows rather than what human demonstrator knows. And when we talk about this ChatGPT, it is sensitive to the tweaks to the input phrasing or attempting the same prompt multiple times. So that's another challenge that has been identified by this ChatGPT. And this model is often excessively verbose and overuses certain phrases, like restating that it's a language model trained by OpenAI and so on. So those were some of the key things and the challenges that we were able to find during this OpenAI experimentation team. Okay, so these were some of my findings as well as the findings from my team. So I hope you have liked it and you have understood about what exactly is this ChatGPT. Don't forget to try out this ChatGPT hands-on and see how it responds to your question. So that will help you to gain more in-depth into the research that is happening in this NLP domain. So with this, we come to the end of this video. I look forward to seeing you next time. So all the very best.
Hey everyone, welcome back to your learning journey. Now in this video, let's talk about the BERT language model. Now when this model was released, that is the BERT language model was released, it actually broken the records of all the previous generation models.
So this model is continuously evolving, and we see this active usage in the NLP community and even in our hands-on learning journey, especially with the help of Hugging Face library. We also made use of one of the BERT model in order to perform the task of sentiment classification. So as we progress in this section, we will try to decode what exactly is this BERT language model, how exactly it is going to work, and how the architecture of this model would look like, and how this model has been trained. So we'll try to understand the inner workings of this BERT language model. So let's start by understanding the activity of sentiment classification using the BERT language model. Now, when we talk about the sentiment classification, that is sentiment detection, if we are making use of the BERT language model, it is nothing but performing the task of classification. So what do we have in case of classification? We have got a model, so we can call it as a BERT language model. And what we will do is, once we extract the features from the BERT language model, we can have a classifier, or we can also have a classifier head. So I can have a ML classifier or a classifier head, and based on that, I'll be able to generate the prediction. So the flow is something like this. For the given text data, I'm going to send the text data to my BERT language model. And by sending this data to this BERT language model, this BERT language model is going to generate the features. So it would generate the features, and using the features generated, I can use the output from the BERT as a features and make use of machine learning classifier and perform the task of prediction, or I can directly fit in the classifier head for this BERT model itself and perform the task of fine tuning. So this is how we can employ it with the help of BERT language model, and the same approach was actually used in our hands-on journey as well. In the hands-on journey, the first part that we had used was we have used this BERT as a feature extractor, and using this feature extractor, we had made use of logistic regression model to perform the task of classification. The alternate approach is using the BERT language model and having the classification hub on top of it, we can actually perform the task of the fine tuning as well. So there are two approaches: feature extraction approach and the fine tuning approach. Now that you know the role of BERT language model and how it is used when we talk about variety of tasks, let's understand the various architecture of this BERT. So when we talk about the architecture, see, the BERT language architecture, according to the research paper, there are actually two versions are available. Okay, there are actually two versions are available. One is a base model. Okay, the another version is called as the large model. So there are two models that we have got. One is base and the other one is large. So what is the difference between the base and the large model? So this BERT base is, you can say that this BERT base is very similar to the transformer architecture when we talk about comparing the performance, and the BERT large model is a very huge model and which actually achieved state of the art results. Now this BERT language model is basically trained on the transformer encoder stack. If you remember the transformer, so in the scenario of this transformers architecture, we actually have both decoder and the encoder, isn't it? We have both encoder and the decoder. Now, when we say this BERT language model, so what it has is it basically has the encoder part. Okay, it basically has the encoder part. We have just made use of the encoder part of this transformer and we have built around the same. That's the clear idea behind this BERT architecture. So this is my transformer architecture, which you are already aware of. Now, what I'm trying to say in this scenario is my BERT language model is actually made up of this only the encoder part. So it's basically a trained encoder stack from this transformer architecture. Let me highlight the same so that you will understand what I'm trying to say. My BERT is made up of the encoder part only. So my BERT is made up of this encoder part only. Okay. Now here, when we talk about this encoder part of the BERT, so what does this encoder part of this BERT is made up of? It's made up of embedding, that is the positional embedding, positional encoding. We have got the multi-head attention, add a normalization layer, and the feed-forward layer. So all these will be the components of this BERT language model. The only thing is, I'll just have the series of encoders. So if I try to break down this base model or any model that I'm trying to specify right now, you can think of it as it has various encoder architectures present behind this. Okay, so I can say that in the scenario of BERT base model, we are actually having total of 12 encoders. Okay, so BERT base is made up of 12 encoder stack, and BERT large is actually made up of 24 encoder stack. So that's the architecture of this BERT model. Okay, so they both have the same model architecture. The only difference is number of encoders that we have over here. Now, this is the high level idea about this BERT model architecture. Now, with this high level idea, let's understand how actually this pre-training have actually occurred. So in the scenario of this BERT language model, we have actually performed the activity of transfer learning. Now in the scenario of this transfer learning, okay, so what we have done is, if you dive into the research paper, okay, if you dive into the research paper, you will come across this transfer learning is actually done with the help of the two tasks, which is called as masked language model and the next sentence prediction. So these are the two things which has been used while performing the transfer learning. So what exactly is this transfer learning approach and how it actually works? Well, when we talk about this masked language model, so this is a special kind of task, or you can think of it as a dummy task. The reason that I'm saying this as a dummy task, because we'll be using this approach to train the model. Then once we have learned the features for a very large data set, we will fine tune it. So the task that we are doing it is just for the purpose of learning as much features as possible. Okay, so when we say masked language model, here the task is just predict the correct word or predict the missing word. That's the overall idea behind this, the masked language model. So what I will have is, I will have a model. Okay, I'll just have a model like this. Okay, so when I'm having a model like this, let's say I've got the text data. My text data or nothing but my input. As you know, since you're already aware of this BERT language model, so let's suppose I'm having a text that look like this. I'll say how are, and then I'll just have a mask over here, doing today, and then SCP. So on my input layer, see, this is my input that I've got. CLS is a special tag that you're already aware of. This is what we specify whenever we are performing the tokenization for the BERT model. And then I have the next words that says how are, and then there is a word that's called as mask, and then it says doing today. So how does the task would look like? So what we'll be doing is, I'll be sending each of the tokens as the input for the BERT. Okay, I'll send each of these inputs, that is each of the tokens, as the inputs for the BERT. Now when I'm sending the inputs together as a parallel, since it's a architecture of the architecture of this transformer, this has the capability to receive the data. So my model is going to generate the output. So the way that I'll be generating the output is something like this. I'll be generating the output in this way. Now in place of masked word, okay, in place of mask, this is an interesting part, okay. In place of mask, what I'll be doing is I'll be predicting the missing word. So I'll draw a box over here. So this is a part, okay, where I'll be predicting what exactly is the word it should come. So maybe when the system is trying to predict, the system is going to generate the prediction for the words that are present in the vocabulary. The top three words are they, your. So these three words are the top three words in the vocabulary. So I'm just giving you an example. It is going to generate the probability for the each and every word that I've got in my vocabulary, and it will try to learn from the given data set using a very large corpus about what is this missing value. Now in this scenario, the missing value is actually you. So this is called as masked language model. So in this masked language model, we are interested in predicting the masked word. That is the correct answer for this example. In this scenario, the word that is you. So this is called as the masked language model. And the another task, another pre-training that has been done right now is the next sentence prediction. NSM, which is nothing but next sentence prediction. So suppose if I have the sentence that says as how are you doing today, then the next sentence will be something as okay, I'm doing good. So here what I'm trying to do is given a sentence A, okay, given a sentence A, predict the sentence B, which is an immediately coming after sentence A. So predict sentence B, which is found immediately after sentence A. So this technique, pre-training technique, is called as next sentence prediction technique. So here, this is the overall pre-training that has been done on this BERT language model. So this BERT language model has been trained to perform these two tasks purely as a way to develop this sophisticated understanding of the language. Now, once the pre-training has been done, that is, once the pre-training or the transfer learning has been done, we actually discard the portion of the model which is specific for these tasks and replace it with something more useful. So that's the core principle behind this transfer learning approach or a pre-training approach. So that's the best part about this transfer learning. And also, when we are performing this transfer learning approach, another best part or another key thing that you have to remember is in this scenario, there is no requirement of label data. There's no requirement of the label data set. The reason is we can actually get the data from the very large corpus like the Wikipedia, or we can just create a web crawler around the internet and we can extract the text data. And here, once we create the language model, we can actually fine tune it for the given task. And when we talk about the BERT, okay, so since we have built a very large model on a very insane high amount of data set, so the task that we can do it is like it is made possible with the level of understanding that we had with this BERT model. Now, once we perform this pre-training, then comes the fine tuning. So here, when I say fine tuning of this BERT language model, so what we'll be doing is once we have got the BERT language model, so assuming that this is my BERT language model, and this BERT language model has 12 layers of my encoder, okay, assuming it's a BERT based model. So this BERT 12-layer neural network that we have got, so this has been trained, at least the first step was MLM and the task of next sentence prediction and the mask language model. So once we have performed this mask language model and next sentence prediction for our task, in order to perform the activity for the required task, then in such scenarios, we will just perform the activity of fine tuning. Now, in the scenario of this fine tuning, we are going to adapt it for our own data set. So that's the best part when it comes to the fine tuning of this neural network. So you have understood what exactly is this BERT model and how exactly the BERT model architecture or the BERT language architecture would look like, and how exactly that we can use the BERT for the sequence classification. So this is what you have learned till now. Now moving on, let's understand some of the basic concepts about this BERT language model. Now when we talk about this BERT language model, so before you deep dive into the architecture of this language model, it is very important that you understand how does the input and the output format of the BERT would look like. Here, when we talk about this BERT, BERT has a way of processing the text that we give the data to it. Even though the text might contain the words that has never occurred in the BERT's pre-training or the BERT's vocabulary, the BERT has the special tokenizer which is specific to that BERT language model, which is capable of addressing those issues. So even when we have implemented the BERT in our previous section, so you might have observed that when I had made use of the word masala dosa, so the masala word was not present over there in the language model. So what it has done was it has split that overall scenario. Let me just represent it so that you'll have a better understanding. So when we had a word called masala dosa, like assuming the word is masala, here when this word masala was not available in the word vocabulary, what it has done was it has splitted this word into the two words where these two words are actually present in my vocabulary. So what happens in the scenario of this tokenizer of this BERT is this will take the raw text data and this would break it into the tokens which this BERT can ingest. And while working, this BERT, it has its own tokenizer. And this tokenizer has its own fixed vocabulary of tokens with an embedding associated with each of the tokens that it has. And here, when we talk about this overall scenario of this transfer learning, okay, so when we talk about the transfer learning, you cannot use your own embeddings. Now, what has been done is, like when this vocabulary has been created, this overall vocabulary has been created by the pre-training that it has actually had. Now, let's say I have come across any word which is not present in the vocabulary of the BERT language model. So in such scenarios, here the tokenizer that was being used is known as word piece tokenizer. Word piece tokenizer. Using this word piece tokenizer, we were able to split the unknown word into the known words of the vocabulary. So that's the overall idea about this word piece tokenizer. And once this text has been split into individual tokens, then the BERT is going to look up for the embeddings for these respective tokens. And these will be the actual inputs to the BERT. So whenever I've got the text with me, okay, so this text will be splitted into the individual tokens and then we will look out for the embeddings. And when we talk about the embedding, that is also a very important concept here in the scenario of this embedding. So this input embeddings is of the vector of the length 768 features. So I will have 768 features in my each embedding. So what happens is, so if you think about this BERT as a black box, then what it does is it's going to take a sequence of embeddings as an input, and then it is going to send out an enhanced version of each of these embeddings on its output. Which means if I want to just represent it in the format of a general way, so just think about it in this way. I'll remove this text, okay, for each of the understanding purpose. So here what you can think about is the BERT model is going to get the input, okay. So it is going to get the input something like this. So how are you doing today? So I'll mention the complete sentence. Okay, it says, how are you doing today? Now, what will be the output of this BERT language model is, the output of this BERT language model is nothing but the output from this embedding. Okay, the output from this, which will be an enhanced embedding. So I'll have the respective boxes for the individual input. So these box represents the embedding representation of my individual word that I have got. So my tokenizer will take this text as an input, break down into the individual tokens, apply the BERT language model, and I'm going to result in the embeddings, and these embeddings, yes, these embeddings will be of the length 768. I hope you are able to make the connection. In our hands-on journey, when we have performed the forward pass using this BERT language model in the previous section, there we had actually got the individual token output, which is of the length 768. Okay, so that is the overall way in which the data is getting processed and how we get the output from this language model. Now, if I want to apply the output to the specific application, we can just use these output embeddings into some other task specific. Then we can go ahead and perform the required activity. So that's the overall idea behind the usage of this language model. So we have seen how does the input would look like. So input will have the text data, will have the additional tokens CLS and SAP, and then we'll perform the tokenization. We will get the, we will go for the embedding. Okay, we'll just make use of the embedding, and using the embedding we'll just go ahead and perform the next task. So from this given text data, I'm going to generate the word embeddings. Okay, we are going to have the word embeddings that will be the given data, given from the data, and from the overall output I'm going to have the enhanced embedding. So this is what is happening in the scenario of this BERT language model when we specify the input and the output. So input is the text data, output will be the enhanced embedding. Now this BERT being a language model which is based on the transformers, so this has the ability to process all the text data in parallel. So since it has all the text data, since it has the ability to process all this text data in the format of parallel, to get a better understanding, let's do one thing. Let's consider a single model. Okay, let's consider a single input, and let's understand how exactly the data will be processed. Now to illustrate this, let's say I have got the text that would look like this. I'll say I've got the input as I love to paint. So this is my text. Let's assume I have performed the tokenization, and for the illustration purpose, I'm not considering the special tokens, but we will be having the special tokens in the backend. So I will have the input, and then on this input, we will have the word embeddings. Okay, we will have the word embeddings. Now you can think of this word embeddings as the sequence to sequence model word embedding. Just for your learning purpose, you can just think in that way. So using this word embeddings, so what I'll be doing is here I'll be let's assume I'm interested in generating the enhanced word embedding for the word love. Okay, I'm interested in generating the enhanced word embedding for the word love. Love is the word which I'm currently interested in. So my model is going to consider the input from all the text data, that is from all the words that I have got with me. Now, once I get the input from all the words of this given data set, so in order to generate the enhanced word embedding for the word love, okay, so what it is going to consider is it is going to consider the various other words that I have got over here, that is the context, which is nothing but the words that are surrounding the love, into consideration in order to generate the output from this model, that is the enhanced word embedding. Now, to learn the context, we will make use of the technique that is called as the attention technique. Okay, that's the overall principle right now. And another common question that learner would ask is when we are working with the text data. So one of the common problem that we get while working with the text data is not every sentence will be of the same length, isn't it? But when we talk about the neural network expects that we have the fixed input dimension and the fixed output dimension. Now that's a fundamental for any of the neural network. Now, in this scenario, how do we deal with this? Well, the first key over here is to recognize that if you just consider the current scenario, okay, if you just consider the given example, so what we will do is we will make use of the concept of the weight normalization. So let me just illustrate about what exactly are we doing in this scenario. See, just think closely. Since in this example we are talking about the highlighted word, that is love. So highlighted word love is my input. Using this word as an input, I'm trying to generate the enhanced word representation of the word love. So that is what I'm doing right now in the scenario of this BERT language model, isn't it? So I'll take the word love and I'll try to generate the enhanced word representation of the word love. So if you consider this word love, so I will have a fixed input representation. So while defining, I can say that, okay, my input will be of fixed size. So I can specify this is what my fixed size will be. Okay, using this input of the fixed size, I'm going to generate the output of the fixed size. Now, if you look into the words that I have got with me, that is the surrounding words, so we call it as a supplemental vectors. So which are nothing but the rest of the words that are present in my sentence, which will help me to generate the enhanced word embedding. So what we do is inside this BERT, the researchers, they have implemented a step that's called as weighted average technique. They have made use of this weighted average technique for all these input vectors. Now, by using this weighted average technique, this has helped us to resolve this issue. So in one way, no matter how many input vectors there are, when we take the average, it will always produce only one output vector. So what it means, no matter how many input vectors, we will always have one out. So that's one advantage. And the other advantage in this scenario is if I simply sum up the vectors, if we sum the vectors, okay, then the magnitude will depend on the number of vectors. So instead, taking their average, the magnitude of result will be much more consistent. So taking the average will result in consistent magnitude. So this is the overall idea behind this weighted average. How do we deal with the variable sentence length? And another key thing that you need to remember when we are processing the data, especially with this BERT language model, is the parallelization. So when we are working with the BERT language model, so the data will be processed independently. That means each word will be processed independently. Now it is possible to parallelize this process and run all the input words through the BERT at a single time itself. So that's the special part. And here, when we are working, so we will have the 12 layers. As I mentioned, the BERT based model will have the 12 layers. So if you look into this scenario, my BERT based model, I've got 12 encoders. So which means I'll take the set of embeddings, I'm going to enhance it, and then I'll use the enhanced embedding from one encoder and I'll use the same thing to the next encoder. So I'll be doing it 12 times. So this is the overall idea behind this BERT language model. So what we have done in this video is we have looked into the deep dive into the aspect as how exactly the BERT language model has been trained and how it takes the input and the output. So we have mostly touched upon the input and output because inside the encoder, it will just go ahead and process the data in an efficient manner. So with this, I'll stop the video over here. I hope this gave you an insight as how BERT language model takes the input and output and the overall architecture of the model. I recommend you to check out the documentation and the research paper around the BERT to learn more about this BERT language model. So I'll try to add more videos on this topic. Do let me know what you think in the question and answers tab. So thank you so much everyone, and I'll see you next time.